Terus langsung rekor.
Selamat siang semuanya, izinkan saya, perwakilan dari Bahasa Global, untuk menjelaskan cara penggunaan fitur interpretasi dalam meeting kita pada siang hari ini. Apabila Bapak dan Ibu sekalian menggunakan Zoom dalam komputer atau laptop Anda sekalian, silakan lihat di bagian bawah ada logo bola dunia, lalu silakan diklik. Ketika Bapak dan Ibu sudah klik logo bola dunia bertuliskan interpretation tersebut, Anda akan melihat pilihan channel interpretasi kami. Apabila Bapak dan Ibu ingin mendengarkan dalam bahasa Inggris atau Indonesia, silakan pilih channel yang Anda inginkan. Ketika Anda sudah memilih, Anda akan langsung mendengarkan penerjemah kami dalam bahasa yang Bapak atau Ibu ingin dengarkan. Bapak dan Ibu tidak perlu klik mute original audio agar ketika pembicara berbicara dalam bahasa yang Bapak atau Ibu ingin dengarkan, Bapak dan Ibu akan langsung mendengarkan suara pembicara secara langsung. Lalu apabila Bapak dan Ibu menggunakan fitur mobile phone atau handphone, Bapak dan Ibu akan melihat tampilan sedikit berbeda. Silahkan klik ikon 3 titik yang berada di pojok kanan bawah handphone dan Bapak Ibu sekalian dalam Zoom Anda. Lalu pilih fitur language interpretation, pilih bahasa yang Bapak Ibu ingin dengarkan. Setelah dipilih, jangan lupa untuk klik done, karena setelah klik done, baru Bapak dan Ibu akan mendengarkan suara penerjemahan. Kemudian kami juga ingin menjelaskan cara untuk melihat tampilan broadcasting yang disediakan dalam Zoom meeting kita pada siang hari ini. Tampilan broadcasting bisa dilihat seperti ada di kotak sebelah kiri. Apabila Bapak dan Ibu ingin melihat tampilan seperti itu saja, Bapak dan Ibu bisa lihat di pojok kanan atas ada tulisan view. Apabila sedang ada share screen seperti sekarang ini, Bapak dan Ibu bisa klik view, lalu pilih standar. Setelah Bapak dan Ibu pilih standar, Bapak dan Ibu bisa klik lagi view-nya, lalu pilih swipe video and share screen untuk menukar antara tampilan broadcasting dan sebaliknya. Sebagai catatan, untuk melihat tampilan presentasi lebih jelas, silakan tetap menggunakan side-by-side speaker agar tampilan presentasi lebih bisa terbaca. Lalu terakhir, sebagai disclaimer yang ada di layar Bapak dan Ibu sekalian, saya juga ingin mengingatkan kepada rekan-rekan co-host untuk tidak melakukan remove spotlight atau mengganti spotlight, juga untuk tidak menghentikan recording yang sedang berjalan. Selain itu juga mohon ketika ada polling yang diluncurkan untuk tidak klik relaunch polling atau menghentikan polling yang sedang berjalan. Itu dilakukan agar acara ini bisa berjalan dengan lancar. Terima kasih atas kerjasama Bapak dan Ibu sekalian. Selamat melakukan meeting pada siang hari ini. Saya kembalikan kepada Mbak Nia.
Thank you very much. Kevin, could you move to the first slide of the day, please? Selamat pagi, good morning everybody in the UK, dan selamat siang rekan-rekan di Indonesia. Welcome to our second day of this training. Whilst yesterday we have heard from Gareth, Mark, Ian, and Gaynor about the issues on UK energy transition journey, as well as the island experiences. Today, we will move to the grid management and technical considerations discussions with colleagues from National Grid, Duncan and Craig, as well as there's going to be Gareth and John as well. So yesterday, we have touched on a little bit around some of the issues raised during the discussions by colleagues in the ministry around approaching to introducing new technology and energy actors and stakeholders and facilitating acceptance and adoption. We've also touched on a little bit around subsea cabling, which can be used to connect between islands and the pluses and minuses within. Hopefully today we can cover a bit more on the grid management side of things, including the transmission reliability after introducing high levels of penetrations of renewable energy, around the capacity of the grid to deal with multiple small scale additional generation and storage assets being added over time, and other issues around including power wheeling and adjustments required when moving between coal-based generation to PPA. So you'll hear some of these issues being discussed in some of our presenters' material. Before we go to those particular material of the day, you have heard yesterday quite a lot about Orkney, the projects that are ongoing, the case examples, and the journey that Orkney has gone through in renewable energy and energy transition. For those of you who have not visited Orkney in person, and those of you who have not visited Orkney virtually, we thought it would be good to share about 4 minutes of what Orkney looks like through this video. Perhaps Tim Bahasa Global, Mas Kevin, could help in playing this introductory video to Orkney, please.
Pulau Orkney adalah kepulauan di utara Skotlandia. Pusat administrasinya berada di Kirkwall. Luas wilayah Pulau Orkney mencapai 990 km persegi dengan jumlah penduduk 22.190. Pulau Orkney gencar melakukan pengembangan energi terbarukan yang ramah lingkungan. Yang dikembangkan di sini antara lain energi angin, energi gelombang, dan pasang surut air laut. Di antara sumber energi yang ada, tenaga angin menjadi andalan pulau ini. Potensi alam yang didukung dengan penggunaan teknologi yang tepat membuat energi terbarukan sukses dikembangkan di pulau ini.
Orkney is connected to our national electricity grid, and we can take energy from that grid, but we can produce energy in Orkney and supply the national down into mainland Scotland and down into the rest of the UK. So we're part of that national grid system. So we are a very good place to produce renewable energy. Some of the most best performing wind turbines in the whole country are built in Orkney. And these wind turbines now produce so much energy that we can fill the cables to the mainland.
Konsumsi energi yang bersumber dari bahan bakar fosil mengandung hidrokarbon berdampak pada pemanasan global.
Increasing prosperity along with increasing population usually means a higher demand for energy. And if we're going to meet our climate change obligations, we're going to need to do that in a more sustainable way with renewable energy sources and also using that energy more efficiently and effectively with smarter buildings and so forth.
Pertumbuhan ekonomi di pulau ini makin bergeliat dengan proyek energi terbarukan yang ada.
We have different sizes, so we have some very big wind turbines, some that are owned by companies. We then have maybe slightly smaller wind turbines that are owned by communities, so they might build have they loaned money to build a wind turbine. But we also have nearly 700 small-scale wind turbines. So these are wind turbines that are under 50 kilowatts. So they're not very big turbines, but they're owned by farmers or landowners or small businesses or even householders that have some land. And they can produce enough energy to supply their house and maybe charge their car if they have an electric car. And then the surplus of that energy is sold back into the grid. So it's providing an income for these people in Orkney. So that's really successful, I would say, in Orkney.
Kini bahan bakar hidrogen turut dikembangkan di Orkney. Tidak seperti bensin atau diesel, pembakaran hidrogen tidak menghasilkan produk sampingan yang berbahaya. BBH atau bahan bakar hidrogen adalah sumber energi masa depan yang bersifat eco-energi.
Selama ini memang Indonesia dan Inggris, UK ada prosperity fund yang memang diperuntukkan untuk pengembangan energi baru terbarukan di Indonesia. Nah, kami sangat mendukung kegiatan ini, bantuan ini, dan kami berharap agar kegiatan-kegiatan yang terkait dengan peningkatan kapasitas, peningkatan kualitas kebijakan, kalau ada pilot project juga diberikan ke Indonesia agar menjadi satu contohan yang bagus yang bisa kita kembangkan nanti dalam skala komersial.
Thank you very much. Kevin, can I go back to the slide for today, please? Thank you. I'm taking you back now out of Orkney, but as Gareth and I'm sure other colleagues in Aquaterra would say, we would love for you to come and visit us one of these days, virtually or in person. That would be a good day for us. So for day 2, which is today, we are running slightly behind our schedule, but we're hoping to cover these 4 topics. So the first one is around renewable energy systems, fundamentals and technology systems descriptions. And the second one will be around introduction to UK grid. And the 5th, for topic 5 and topic 6, Duncan and Craig will speak about the electricity network integrity, reliability, and renewable energy integration. Next slide, please. So the first topic, Gareth will speak about renewable energy systems technologies, and this will consist of the following issues. Next slide, please. The overview of the different technology, green and blue technology, the advantages and disadvantages of those technologies in relations to the place that will use and benefit from these systems. So Gareth, over to you. Just a quick reminder, sorry for colleagues, participants to please put forward your questions on the chat box today. If you need to speak in Bahasa Indonesia, please welcome so, or give your questions in English. We will also have a discussion and question and answers sessions after Gareth presents, so we could also discuss some of your questions and comments there. On to you, Gareth.
Thank you, Nia. Good afternoon, everybody in Indonesia. It's great to see so many of you coming back for the second day. So I'm just going to share my screen and we can get started. So I have 2 tasks today, which is first of all to look at a range of renewable energy technologies and then to look at some of the pros and cons and the advantages that are associated with these technologies. And I'm going to undertake that in the context of particular places in Indonesia. So to start off with, what I'd like to do is just get us to think about the context for renewable energy in Indonesia. And on this slide, it basically reflects the fact that Indonesia is an archipelago of islands. And so, yes, there's an abundance of what might be called green energy, energy that comes from the land and associated with the land. But also you have an incredible breadth of sea and water area. And that's where blue energy energy associated with water comes to play a part. And what this slide shows is that these are not just two realms, because each part of the land and each part of the sea has different attributes. If you're in the middle of Jakarta or a big city, you need lots of energy in big packages to provide the energy needs. If you're in a small remote community in rural Indonesia, in the highlands of the mountains, or if you're on a small island, you need much smaller packages of energy to meet your needs. And so this range of sizes is indicated on the vertical scale. And the other factor around energy is that it isn't all the same price everywhere you go. Different places in Indonesia have different electricity prices. The price of the diesel or petrol that you put in your vehicle or in your scooter or in your boat also varies across Indonesia. And the price of industrial energy also varies from place to place. So the energy market is not just one market, it's actually lots of different markets that reflect the different prices that you have to pay for that energy. So we have these two scales or gradients, one around the amount of energy that's needed in a particular market, and also the price that you pay for energy. And I think that's a useful context to then think about the technologies that might be appropriate in each of those areas. So if we first think about onshore, I've picked 4 topics here: wind, solar, geothermal, and biomass. And basically there are renewable energy technologies that meet each of these size ranges that I've just outlined. So in wind, for example, you can have very big wind turbines of over 1 megawatt, but you can go down through the scales, as Ian was describing in the video, down to maybe less than 5 kilowatts. And each of those technologies is suited to a particular situation. And the same is true in a more modular way with solar. A solar panel is a kind of basic unit of a few watts of energy, but you can multiply those solar panels up to create megawatts of capacity in a particular location. When we think about geothermal, there are opportunities for what are called ground source heat pumps, which might be on a household scale, but then you can get up to major geothermal plants associated with particularly volcanic activity, and the same is true with biomass. So there are a range of technologies that can meet those different scales of market. And if we turn to the blue energy areas, an aquatic technology, again, we can see a similar range of scales. So here we have tidal currents, waves, offshore wind, hydropower, floating solar, and aquathermal. And what we can see here, again, on that vertical scale, is that there's different technologies that can meet these different size classes associated with the marketplace. So we have a number of technology tools that we can use, and the challenge is to think about which is the most appropriate technology in the particular market situation that we're examining. Now, the other part that's important is around the variability of renewables. And in fact, although this is a label that's often given to renewables to say the problem with them is that they're variable, in fact, if you look from supply right the way through to demand, all energy sources are variable. Oil, gas, coal doesn't come to the customer in an easy flow. You have to gather it, mine it, produce it, store it, then convert it to electricity, and then pump that electricity to people's homes. So there is a storage mechanism in that supply chain. So then it's not surprising that when we come to renewables, we have to think about where storage can be introduced into that option as well. So there are a range of technologies such as batteries, such as molecular storage through hydrogen or ammonia, which can be applied to that issue. And there's also a range of places along the supply chain of energy at the bottom here where that storage can be applied. So you can apply the battery at the source of generation, or you could supply it in the middle of that process or at the point of end use. And in fact, as we go forward, it's likely that storage will be introduced in all of these places as appropriate in the particular energy system. The other point to make is that although there's a lot of technologies that are emerging in terms of the smaller scale storage, when it comes to longer term system balancing and storage, that's still a technological gap that needs to be filled. Okay, so let's move on now then to think about how we can maybe apply these in the context of the blue economy. So what do we mean by blue economy? Sorry, are you getting a headphone, or it sounds okay at your end? I'm getting a feedback on my microphone. Is it okay for you though?
You were there was some time that I received a feedback as well. So Mas Kevin from Bahasa Global, can we confirm that the issue is addressed?
I think it's better now. I think because it's from.
Okay, I'll try again. And if
No
just raise your hand if it comes problem again, Nia. Okay.
Yeah.
Yeah. So I wanted to look at the blue economy because within Indonesia, there's a lot of work that's been done on terrestrial energy and meeting terrestrial energy demands. But when you come to look at the whole breadth of Indonesia, first of all, there's incredible resources and industries associated with the sea. But also you have communities, coastal communities dominate Indonesia, and communities on islands and smaller islands have yet to be totally served by the energy system. So this idea of powering the blue economy is an incredibly important focus going forward alongside powering the green economy. So the first technology that I'd like to focus on is offshore floating wind and wind. And here you can see the progression from shallow water, where you have the turbine embedded into the seabed, then building a jacket to support the turbine, and then moving into the floating wind realm. And all of these technologies are now being deployed around the world. So if we look at the UK in terms of founded wind, offshore wind, the UK has just completed a 1.2 gigawatt project called Hornsea, which uses relatively large turbines, 8-9 megawatt turbines, and many of these to create a huge infrastructure to support our electrical system. But what we're also seeing now is the adoption of new floating wind technology, which takes that opportunity into slightly deeper water. And this may be something that's of interest in Indonesia, although the main areas for offshore wind in Indonesia are associated with an area off West Papua and off the southwest tip of Sulawesi. And in these areas, there is actually shallow water. That means that founded turbines will probably work there. But what is interesting about this offshore wind technology is, although it started off at quite a high price, the price of this is lowering and lowering. And now in the UK, offshore wind can be produced more cheaply than onshore sources of energy. So it's becoming price competitive. But as well as the turbines themselves, we need to also think about ongoing efficiency. And what this slide is showing is that the scale of offshore wind technologies is increasing all the time. So when I showed you the Hornsea development, the turbines there are under 10 megawatts in size. But the next generation of turbines that people are looking to deploy are going to be 15 to 20 megawatts in size. And you can see here on the left-hand side, the size of the nacelle. It's absolutely huge compared to those people there. So if we're going to be deploying that scale of technology going forward, and that's a 12 megawatt machine, we need new infrastructure to be able to handle that. And one of the activities that we're involved in at the moment is looking at developing new floating port concepts, as shown on the right-hand side here, to be able to assemble and deploy large numbers of offshore wind turbines, and particularly floating turbines. So you can see that offshore wind, for example, is becoming price competitive, and the range of technologies is becoming ever broader. Another area that Pat Chris focused on yesterday was the importance that Indonesia is now realizing floating solar will play. And here we can see some floating solar developments on fresh water. So places like China in particular are really embracing this as a major source of energy. And you can see the large scale developments on the left-hand side there. But there are also places where smaller scale developments are being looked at. And the one on the top there is in Sri Lanka, using a design from Norway. And you can see that that's quite a modular packaged system that could perhaps support smaller communities. And the bottom slide there on the right is from Singapore, where there's a test center where different types of technologies can be tested. So all of these facilities are on freshwater, which is where this sector has started. But there's a great deal of interest now, sorry, before I get there. And in terms of the deployment of these solar panels, here you can see some panels actually being deployed in the UK, which show how easy it is to float them out. And this modularity and the simplicity of construction is one of the factors that makes floating solar really attractive. But as I was saying, moving on from freshwater, what's becoming increasingly interesting is the application of floating solar in a marine context. And so there's a number of companies that you can see here deploying small and larger scale arrays of solar panels into marine environments. And we think that this is a particularly interesting opportunity for Indonesia for providing energy, as you can see there in this swim sol example in the top left, to small remote islands which have a few kilowatts of demand, which can maybe be met through that floating solar technique. Just to touch on two other areas of blue energy. One is tidal energy. So there's a range of technologies that you can see on the left-hand side here, and how they exploit the movement of water through rotary actions or aerofoil actions. And one of the things that's really positive about tidal energy is it's very, very predictable about when it will be generated. But one of the other things that we have to think about is that it's also quite variable. And the data on the right-hand side shows that for the islands of Scotland, for example, the way in which tidal energy varies over the space of a month. And this is in relation to the sequence of tides, which you can see at the top there, relating to the movement of the moon and the sun around the earth. And this creates spring and neap tides, which lead to predictable but variable outputs. But there are significant progress being made in this tidal sector. And what I've gathered here are the machines which in the last 6 months have been deployed around the world and are operating at the present time, and producing power into their local grid systems and for other purposes. And also, I couldn't forget about wave energy, and particularly in Indonesia, along the coasts of Sumatra and Java and as far as Bali and Lombok, then there may be opportunities for using different types of technology that are exploiting the movement of waves. And these, rather than being rotary technologies, tend to be objects that move up and down with the motion of the waves. And again, there are a number of actual technologies now being deployed around the world, demonstrating the capacity for generating power from the waves. So again, progress being made, maybe not as much as in tidal energy and not as much in floating solar and wind, but all of these technologies are now making progress. So what I wanted to do in the last part of my talk is look at the advantages and disadvantages of these technologies. And what I want to do is think about that in the context of place, because so many times people talk about the advantages and disadvantages of technology without thinking about where they're going to be deployed. So I showed you this map yesterday, which shows the distribution of some of the key onshore and marine resources around Indonesia. And what this indicates is that in different places and different parts of Indonesia, solar power, wind power, wave power, and tidal power may have different levels of importance and suitability. And I mentioned at the start of the presentation that we have different markets. And so across Indonesia, there's a range of market opportunities. The number of people and the number of communities where people live is variable, and the size of those communities varies. The presence of the mining industry, the wood pulp industry, the prawn farming industry, fisheries activity that might require refrigeration, the availability of water, aquaculture, all of these things change across Indonesia, and there's specific places where these activities take place. And then if we go to transport links and strategic uses such as oil and gas or military applications, then again, these happen in specific places. And what's also interesting here, and you can see at the bottom here, these numbers, the value of energy for these different markets is also variable. So in the urban situation where there's grid connected electricity, the value of energy might be down as low as $50 per megawatt hour. But when you come to those specific areas of high strategic importance, the value of energy can go up very high, maybe as high as $1,000 per megawatt hour. So the amount of energy you need at that high value may be much less. So there's a much greater volume of energy at the low price. And in the way in which we deploy technology, we need to weigh up the amount of energy that's needed and the price to come up with the right technical solution. And if we think about that value versus size scale, I think in the context of blue energy, we can come up with this scheme, which shows the application of different technologies in different combinations of size and value. And what this indicates is that floating solar is actually the most universal of the technologies in terms of its application. But for example, offshore wind is only going to work probably at larger scale and be limited in that area. So that shows us two examples where technologies have different profiles within the market opportunities that exist. So if we look now and dive into some specific opportunities, and the first one I've chosen is to look forward to the new capital and that as a location. And the question I've asked is, what are the renewable energy opportunities associated with this particular site? And what you can see in the table below is that there are floating solar opportunities nearby. There are some limited tidal opportunities, but there are also aquathermal opportunities. So these are from seawater air conditioning and from OTEC, ocean thermal energy conversion, in the straits between Kalimantan and Sulawesi, where there's cool water, oceanic water coming in from the Pacific Ocean. So there are particular options for energy generation associated with this future site for the new capital, and it will be interesting to see over future months and years how these different renewable energy resources are harnessed for that project. Another place that is interesting to look at is the town of Larantuka on the eastern edge of Flores. And this is a community where it's right beside a tidal stream, but also it's a very sunny place. So it's not just tide, but floating solar that could perhaps play a role here. And on the north side of the island, you have access there to deep water. So a combination here of perhaps tide and floating solar allied to some thermal energy capacity could provide a solution. Now, this is an area that we have done some work in, but when Gaynor described this yesterday, she actually suggested that we've actually deployed tidal turbines in this area, but that was actually a little bit of a mistake. She got a bit muddled between Bintuni in West Papua and Larantuka. So there have been no turbines deployed in Larantuka at this point. It's just study work that has been done. Another concept or scale of development, it would be in a smaller community, such as the islands in Wakatobi. And here the options in terms of technology are perhaps less. And what we see here is that there are probably ideal opportunities for floating solar rafts. So you can see in this fishing village here that a new walkway has been built recently, but there's ideal opportunities for rafts of floating solar to be right beside people that need that energy in the fishing community and in the adjacent township. So there's smart solutions that match the needs of the people. And the fact that urban development has taken place close to the sea suggests marine options are best. And if we go down even smaller in scale to places like Takabanarate, where it might be very small townships of 100 people or less, again, floating solar is probably the option that comes out best. It's scalable. It can be produced at a modular scale, which might produce enough for lighting and communications. You don't need a lot of energy to transform the lives of people in these areas. But it can also be scaled up as maybe refrigeration is used for supporting fishing activities, etc. And if we move away from residential use to industrial use, this is the location in West Papua where the tidal turbine has been deployed to support a wood pulp enterprise. But interestingly, alongside that tidal potential, there's also options again for floating solar, although the levels of solar radiation here are less than there are, for example, in Larantuka. But as you can see here, the concept for deployment involved a raft, which is on the surface. And although you can deploy the turbine underneath the raft, you could also, in a production condition, produce solar panels on top of the raft to produce solar energy as well. So that combination here of floating solar and tide may provide the best solution. And we talked yesterday about the importance of thinking about transport as well. And road transport and ferry transport are very important in a number of island situations. Here I've taken Lombok and the straits between Lombok and Bali as an example. And producing energy that could be used by the fast boats which take tourists and residents back and forward between these communities, and providing sources of energy for electric vehicles and electric scooters going forward. And as Pat Chris said, Indonesia is thinking about actually building these vehicles as well as supplying the energy to them. There's an opportunity there. And I think that what is interesting about transport is that each of the vehicles has its own storage tank with them, or its own battery associated with it. So the variability of output from renewables is less critical when it comes to supporting transport. And so a number of technologies might be able to play a role there. And if we go to a slightly larger scale of transport, to the many ferries that cross between the islands, and here I've taken the Sunda Strait between Sumatra and Java as the example, these vessels may need between 5 megawatts and 25 megawatts capacity to push them through the water at the speeds required by the passengers. So there's greater levels of energy needed per ship, and another opportunity there to use different technologies for that purpose. And at another scale, again, if we start to come to larger industry, and thinking here about the metal smelting industry. So Indonesia is making this move from producing metal ores and exporting them to other countries for processing, to having greater levels of processing and moving up the supply chain locally in Indonesia. But there's a choice in terms of these smelters as to whether they're powered by coal or they're powered by electricity. And in many other countries where coal is less prolific, or that people have moved away from coal, electricity is the tool of choice. But at the moment, the plans for many of these smelters are to fuel these through coal. And there's an opportunity then for that to be changed as part of the transition away from coal. So it's not just grid connected electricity, but it's industrial uses of energy as well. And a range of technologies, depending on the place, can play a role there. And to look more specifically at an example is the Morowali Industrial Park on the eastern side of Sulawesi. And here, there's a huge industrial complex which has been built up over the last 10 years. It has a power station associated with it just to provide power to this site, and that's around 1.5 gigawatts in scale, 1,500 megawatts in scale. Now, if we look at the productivity of, for example, solar, you'd need 7,000 megawatts, 7 gigawatts of solar equivalent. And what I've shown in the maps below is 2 areas where floating solar options could sit alongside the current industrial plant to provide that power. So one is on an inland lake and the other is in the coastal sea areas. So within a 20-kilometer radius of this site, we have renewable energy capacity that could be providing the power to this huge industrial complex, which would mean that the coal that's currently imported to support it could become redundant. So obviously from an environmental climate change perspective, that's a really important prospect. But as well as industrial energy and electricity, there's also the grid connected electricity. And we touched yesterday on the ambition in Indonesia to start the transition to initially support and eventually replace coal power plants. And I've picked an example here in Cirebon, which has 2 plants next to each other, an existing plant here and then a new site being developed here. And you can see the coal that's being imported to these sites on the existing plant, and the similar arrangement will happen here on the new plant. But what is also interesting is that this being near to the sea provides an ideal platform and operating base for potentially a coastal floating solar plant. And I've shown here the area that would be required to install 200 megawatts of floating solar potential along the coast. So through these 5 areas, you could get to 1 gigawatt. And if we zoom out a bit more, we could see, for example, potential for perhaps 10 gigawatts of floating solar potential just in this bay in Indonesia. And the importance of this location is that it then links to a strong grid connection which exists for the existing coal power plant. So we have the option of installing floating solar right next to existing coal infrastructure, which means that the grid that is there at the moment can be used. And this can be done in a transitional way. So you can start off with a small amount of floating solar and then increase it as demand increases and as the phase out of coal continues. So it's not just a change it overnight job, it's something that can be done over time.
Gareth, sorry, just to remind you, you have about a minute left, and
Yep.
we're running late already. Thank you.
Yeah. So this is just getting to my final shots now. So applying that concept across Indonesia, this map is just some of the coal power plants that exist across Indonesia. And what we've done here, which are shown by the yellow dots, and also interestingly, coal production in the Malay Peninsula. And what we've then done is looked at the types of, in this case, blue energy resources, which might be able to be used to support these power stations and in time replace their dependency on coal. And what you can see is a lot of floating solar symbols. You can see some tide, a few offshore wind symbols, and some aquathermal in a few places, and maybe some wave energy as well. So detailed studies need to be done to see how that could happen, but it's very clear, I think, that floating solar could provide a very robust alternative to the coal that Indonesia is currently dependent on. And I mentioned yesterday that as well as domestic demand, we also need to think about the benefit that comes to Indonesia from exporting energy. And if we look at that relationship between Indonesia and the Malay Peninsula, where there's an incredible demand for energy, maybe it's worth focusing also on not only supporting Indonesia's electricity demands, but also thinking about how Kuala Lumpur, Malacca, and Singapore could be supported through Indonesian energy exported from renewables, and particularly from floating solar. So we're going to talk a little bit more about this tomorrow in terms of what could this type of technology mean, but I just wanted to give you a foretaste of the scale of development that we're beginning to see through this work. So if we look at the patches of sea that could develop and support energy production, in terms of offshore wind, we see an incredible potential of particularly West Papua in the Arafura Sea, and that could amount to 400 gigawatts. But there's also capacity for floating solar, tide, aquathermal, and overall that could give over a terawatt of installed capacity. So this would help Indonesia fulfill its renewables dream of basically decoupling its economy from the carbon-based sources that we have at the moment and helping to achieve its net zero ambition. Terima kasih. Thank you.
Thanks very much, Gareth. Mas Kevin, could you open the poll, please, after this topic? That's great. If all participants can participate in this poll questions, that would be great. And in the meantime, can I remind everybody again to please fill in your attendance list, because that will be used to determine your completion certificate. So that would be most appreciated, and the link should be provided on the chat box by Great Britain. Mas Kevin, could you check the polls, please? There's a miss. There we go. Thank you. Apologies, everybody. This is the correct poll. Okay, so whilst the participants are completing this poll, in the interest of time, can I maybe just take the first question? There are a couple already put through in the chat box, so I'll read one of them to you, Gareth, and hopefully we can cover a couple before we move on to the next topic. The first one is, Dear Mr. Gareth, I would like to know what you think about the risk of the offshore floating wind turbine and the floating solar in marine space, considering that Indonesia is one of the countries which is prone to tsunami. Will it give greater risk if the technology is applied in Indonesia?
It's a good question. I mean, all of the energy infrastructure that's provided on the coast or on the sea is going to be subject to that risk. So the existing oil and gas sector, coastal power stations are already vulnerable to tsunamis. So that would be a key factor in determining the suitability of areas for development. And in terms of floating or wind, and in the coastal areas where the water is shallow, this will be founded wind. I actually think that a turbine could be developed which would be relatively robust to, virtually all tsunami type events. Floating solar is going to be a bit more difficult, but those events are so devastating that in many cases, there is a degree of infrastructure sacrifice associated with that. So it may be a question of at least making sure that any floating solar array didn't move inland. So it basically, if you like, sank to the seabed, but it might need to be replaced afterwards if that was used. But I'd also say that different parts of Indonesia have different tsunami risks, and there are quite a few parts where the arrangement of the land versus the sea versus the fault lines where the earthquakes take place would mean that you could have sites that had virtually no or no tsunami risk as well.
Thanks very much, Gareth. And this is the last question for now. This is in Indonesian, so I'd ask the translator to help in translating this to English. Bapak Gareth, bagaimana pengalaman UK dalam hal operation and maintenance pembangkit listrik yang dibangun di pulau-pulau untuk menjaga keberlanjutannya. Apakah pemerintah atau swasta yang memegang peranan besar atau ada skema tertentu yang mendorong komunitas setempat dapat mandiri dalam ONM? Terima kasih.
So it's a mixture. One of the things that we've tried to do is to evolve our energy system. I think, as we touched on yesterday, our historical energy system was quite centralized. And what we've tried to do over the last 2 decades in particular is to build capacity across our rural and island communities to be able to embrace new forms of energy. And rather than that being pushed out from the center, it's very often been the periphery which has been saying, look, renewable energy is good for us. Let us have it. We'll build the capacity for it. So in many cases, it's been a community-led initiative. So we see the same in Indonesia. You know, when you go around and you meet people in remoter parts of Indonesia, they understand the challenges they have with energy. So they have a desire to get better access and better solutions. And so empowering the people in these places to be absolutely core to the solution is crucial to it. And that means developing skills and understanding to be able to work with the technology. The one thing that none of us can afford to do is deliver alien technology into remote locations and just expect it to happen. You know, there's many instances of that where technology has failed. So working from encouraging the community to be active in that, but also with the support and supply chain from more industrialized centers is going to be a balance to be struck.
Thanks very much, Gareth. Okay, can I ask Mas Kevin to close the poll, please? Okay, so about 58% of you have indicated that you have not had any experience working in the renewable energy. And then the second one would be the renewable energy resources that you know and would be relevant to Indonesia. Most of you agrees that it is solar energy, and closely followed by geothermal and water-based resources. For the third question, the result of the poll shows that the skills related to renewable energy currently that you think will be relevant to your current positions, most of you indicate, 60% of you indicated that it's around the planning, regulatory and legal systems, and followed closely by technical. So that's the spread of what people are thinking about the questions presented in this poll. Okay, so in the interest of time, can I move to the next slide, please, Kevin? Okay, so this next topic will be presented by John, and John will cover a number of issues today. Next slide, please, Kevin. Can I have the next slide, please? Thank you. And this will include systems approach, principles and codes and standards, and designs principles. So again, it was great to see the questions and comments coming through the chat box. The ones that we haven't been able to address, we will get back to you and disperse around the participants after the event concluded. But yes, if you keep doing that, that would be perfect. John, the time is yours.
Okay. Thanks very much, Nia, and good afternoon, everybody. It's a pleasure to be here today. I'm just going to try and share my screen, and hopefully we can work from my slide pack then. Nia, can you just confirm that's come through okay?
No, it has not actually, John.
Okay, sorry, just try again.
Yeah, we can see that fine.
You've got that now, right, brilliant.
Yep. Thanks, John.
Is that okay?
Perfect.
Okay, that's great. Thanks very much. Yeah, so good afternoon, everybody. So it's a pleasure to be here. What I'm hoping to do is provide a bit of a link between the presentation that Gareth's given there on the renewable energy technologies and how we can apply those to different areas, and the presentation that Duncan and Craig are going to give on the UK national grid side of things. So I'm going to try and cover these three areas in I guess in three parts. So I was going to start looking at just large power systems and how they work, then sort of bring it down to a local level. And I appreciate you've heard quite a bit about Orkney, but I was just going to talk a little bit more about some of the work we're doing there around the grid. And then I'd close the session just by looking at some of the sort of codes and standards and how we're using those in the UK. So somebody started life actually as with my training in coal-fired power stations. I was going to start just by looking at the large energy systems. And really at the simplest level, they're about bringing these sources of energy, a whole range of sources, whether that's gas, coal, biomass, together to the users basically. So we're getting the energy from the source through to the users. And globally, there's a massive amount of infrastructure associated with that. Whether it's ships, whether it's pipelines, to do that. However, as we look to decarbonise on this journey to address the climate emergency, we can see that whilst the sort of raw molecules, if you like, chemical energy that we have in things like fossil fuels, we'll still need to decarbonise those. A lot of the effort is going to be taken by the electricity sector. So we're looking to move more and more of what we use into the electricity space. In the UK, we've made a lot of progress, as you'll have seen, in terms of making that transition. Last year, we generated about 40% of our electricity from renewables, but electricity only accounts for about 20% of the energy that we actually use in the UK. The remaining 8% largely used in our transport, and for us in the UK, heating our homes and properties is still very much dominated by the fossil fuel sector. So we've done a lot of renewables as part of the other things we're looking to do over the next 4 years. We're looking to build another of the world's biggest offshore wind farms. So Gareth talked about Hornsea there at 1.2 gigawatts. The next wind farm off Dogger Bank, which is about 100 kilometres off the east coast of the UK, is going to be about 9 gigawatts in total. We're looking to ban the use of gas in homes from 2025, and we're looking to ban the sale of petrol and diesel cars on our roads from 2030. So just looking at the electric system in a little bit more detail, I thought just to look back at how it works and really how we transport the electricity around. A little bit of theory for you, but hopefully that will help when you get the presentation from Duncan and Craig. So just as a quick analogy, just looking at on the left-hand side, this analogy with water. If we want to fill our bucket of water and basically shift this energy, we can either increase the pressure, so we can raise the height of the tank on the left-hand side, or we can increase the diameter of the pipe. So we basically either put more pressure behind the water to make it come out faster, or we increase the pipe to make it flow faster. Sorry, to make more flow. So there's two ways. That's the analogy to electricity. There is if we increase the height of that water, that's equivalent really to increasing the voltage on the system. Whereas if we increase the flow, that's equivalent to the current. The reason I mention this is just to explain that the reason we use high voltage electricity is because if we try and increase that flow, which is equivalent to the current, we increase the losses, and that relationship is squared basically. I'm pretty sure a lot of you'll be aware of this. But if we increase that current, we increase the losses. So double the current, we increase the losses by a factor of 4, which we don't get that effect by increasing the voltage. So basically, it's better to transmit electricity at higher voltages. The challenge then is that, like lightning, higher voltage electricity likes to jump around a lot and likes to get down to earth. So we end up then having to put bigger insulation around our conductors, or bigger spacing between them, so it can't jump to earth or jump to other conductors. Next slide is just looking at why we use alternating current. So we've talked obviously a fair bit about conventional forms of generation and coal-fired generation. The reason we use alternating current, there's 3 main reasons. If we look at an electrical generator, the central part of that generator, which is the part that rotates, is driven by, say, a steam turbine in the case of a coal-fired power station. And we're able to take the power off the outer part, the stationary part, and it basically provides this nice sinusoidal profile, which you've got at the top right there. So we can get all the power off the outside without having to take it off the inner rotating part, which is it's easier to do. If we've got lots of generators, which we have with coal-fired generation, for example, we can lock them together so they all rotate and all lock onto that same waveform. And that's really why we call them synchronous generation. And that's why conventionally in power systems, we like this type of generation, because all the generators are locked together. They'll follow the same waveform at the same voltage and the same frequency, a lot of rotating mass. And then as the load on the system changes, so if load goes up or load goes down, all these generators work together really as a single generator, and they can flex really well. So conventional power systems run very reliably because of this. We can also change the voltage. So we've got this principle, what we call electromagnetic induction. So we can change voltage levels at AC because the voltage is changing. We can change the voltage from one voltage to another relatively easily through a transformer. And the efficiency of that process is very efficient. It's like 99% plus efficient. So it's relatively easy to do. The other big benefit of AC, of alternating current, compared with DC, is that because it's a cyclical profile, as it goes to zero, so the voltage goes down to zero, we can actually open a circuit far easier than if it doesn't. So if you've got a DC supply, it's really difficult to open and close a circuit because you get a huge amount of arcing, and that can cause a lot of damage to equipment. So an AC system is really good for basically building an internet-connected electricity system. I appreciate it's widely known, but it's just a bit of a refresher for the subsequent sessions. So just the benefits of using AC in the way we transport electricity around. So it's the way we generate electricity, the fact that we can transform it, and then the fact that we can control it and build an interconnected system. That's not to say direct current doesn't have a part at all. It's been around for probably longer than alternating current, and it has been used across power systems across the world. And it's really got some significant advantages over AC, and it's certainly got an application in modern power systems. The main advantages of AC is that we can transmit more power, so we can get more power down the same cable size compared with AC. And the other big benefit is that we can use it to link two systems. So if we've got two countries operating, for example, at different frequencies, or not in phase with each other, so one country's at 50 hertz and one country's at 60 hertz, we can tie those two countries together with DC and change the power between them without having to synchronize them. So we're not having to synchronize two big generators. The other benefit of that is that a lot of the renewables, certainly wind, it's best if the rotational speed of the wind turbines is linked to the wind speed. So that wind is variable, so the rotational speed is variable. So the frequency at which we generate from wind turbines is variable. But if we put that through basically a DC link first, and then connect it to the grid, we can allow the wind turbine to operate at its most efficient, but still connect to the grid and support the grid. The other benefit of DC, because you don't have these peak voltages, generally need less insulation as well. DC is becoming more common in terms of our production. So certainly in terms of solar PV, that's a DC source of generation, and to connect that to the AC network, we need to convert it from DC to AC. But you can couple up PV directly with battery energy storage systems on the DC side. So that has the advantages of not having to convert from AC to DC or back again. This conversion process, and it's become something we've had to manage more over the years as we've introduced more converters onto the system, does create what we call noise or harmonics. Now the power electronics we use today are a lot more sophisticated than those that we probably used 30 years ago, and the level of harmonic content from them is a lot less. But that needs to be designed in and filtered out in systems, otherwise it can become a nuisance both for the system itself in terms of creating heating problems on the system, but also for users and things like voltage flicker on their supplies. So just a quick recap on that. if we go from our conventional power system, where we've had large centralized synchronous generators with providing a lot of spinning inertia that you're able to cope with changes in load and bulk transmission. And that generation has largely followed the demand on the system, but it's been significantly reliant on the use of fossil fuels. So as we move our power systems, and Duncan and Craig will talk a lot more about this in terms of the developments in the UK, there's significant more distributed generation and variable generation, as Gareth talked about there, and a lot of that generation is non-synchronous. So it's connected to the network through a DC link. It doesn't lock onto that same AC waveform. DC is more widely used for bulk transmission. So I'll show you some examples in the UK on the next slide of where we're starting to do that more and more. We're also looking at smarter loads on the network. So instead of passive loads that we generally had, we're looking to make loads more dynamic. So whether that's electric vehicles, for example, and the charging of those electric vehicles and having control over when those electric vehicles are charged. Data modeling and forecasting is becoming increasingly, or it's more and more important, and you'll see some of the developments in that over the last 10 years. And energy storage is becoming increasingly important as well, both at a local level and at a national level to match this supply of electricity with demand. Fundamentally, security and cost has always been key to the design of a power system. So reliability of supplies and trying to deliver supplies that are affordable. But obviously decarbonisation is where a lot of the effort is now, whilst not compromising cost and security. So if we just look at the UK power system and how that's changed over the last 30 years. So this diagram on the left-hand side shows the network as it is now. In that time, we've added almost 14 gigawatts of onshore wind. That's about 9,000 turbines that have been installed in the UK across over 2,500 projects. Offshore, we've deployed about 2,300 wind turbines across 39 projects. The project that Gareth mentioned with the 7 megawatt wind turbines, the next one, the big 9 gigawatt project I mentioned earlier, is looking, I think, at 13 megawatt turbines. And to support that project that we're building, I think it's the biggest vessel in the world specifically for that project to deploy the turbines. On solar PV, we've deployed 14,000 megawatts. Around about 2/3 of that is ground mounted. I think there's a small element of floating within that, and about 1/3 of that is rooftop solar on homes and offices. We've increased the level of interconnection. So 30 years ago, there was a main interconnector with France, which is shown down on the bottom right-hand side of this diagram. That was a 2 gigawatt connection. We've added connections of a gigawatt, a further gigawatt to France, Belgium, and Netherlands. And we've also added 2 500 megawatt connections across to the island of Ireland. We've gone from a system where pretty much all the generation was connected at transmission level, so basically centralized generation, to a system now where 25% of our generation is actually connected at a distribution level or a local level. And over that time, we've pretty much decommissioned all our coal-fired capacity. So there's over 40 gigawatts of coal-fired generation. I think, as Alex mentioned yesterday, I think we're down to 1 power station this year, I think now, and then by 2024, we'll have no coal-fired power stations on the system. We've gone from a largely centrally controlled, publicly owned electricity system. So across the transmission and distribution and generation, that was really in the hands of 15 companies or 15 organisations which were owned by the government back in 1990, to now where we've got hundreds of companies or participants. And over that time, electricity consumption has largely unchanged. Mainly through whilst overall demand has probably increased, we've been very good at improving our energy efficiency across properties. So things like low energy lighting, for example, has allowed us to maintain that electricity consumption. But we expect that to increase over the coming years as we seek to decarbonise our heat and transport sectors. So just a quick look at the growth in renewables, I think you've seen a little bit on this before. This was up to 2019, where we were at 37%. Let's say last year it was about 40% we generated from renewables, and you can see it's widespread around the UK, both in terms of this is offshore and onshore wind capacity. Bit of a northerly bias in terms of the onshore capacity, mainly due to the wind speeds being higher in the north of the country and less population. Okay, just bringing this down to a more local level, and what we're doing in Orkney, and just talk about 3 areas. In terms of Orkney at the moment, Orkney lies at the extremity of the UK grid network, and it has high levels of wind, so that we generate more electricity than we actually consume on the island. Now, the way we could control that one time was just basically quite a crude, quite binary approach, would just be to switch off wind generators. So around about 10 years ago, the system moved to an active network management, which Mark talked on about this a little bit yesterday, but basically that was looking at basically controlling the output of those wind turbines. So we would look to bring down the output in a controlled way to try and match demand. And that was driven by pinch points on the network. So if those pinch points were seeing an excess flow, so the grid was being stressed at those points, then we could pull back the generation the other side of those pinch points so that the network wasn't overloaded. What we're doing with the Reflex project, which you've heard a little bit about, is we're trying to work not just on the generation side, but also on the demand side, and introduce energy storage, so we can really sort of maximise the use of the local grid. And in doing that, we're hoping that will actually accelerate decarbonisation, particularly in the heat and transport sectors, and at the same time try and deliver affordable energy to residents and businesses in Orkney. The smart local energy systems, as we call them, they're still very much part of the wider system. So Orkney will still remain connected through these 2 cables to the UK mainland system. Just to give you a quick flavour of the challenges we face in Orkney, this is just an autumn day from a few years ago. The blue line represents the local demand on the electricity system, and the red line shows the output from the renewable generation sources. So you can see we've often got output from generation, which is 2.5 times that of the local demand. And the way we balance that really at the moment is either by trying to either pull back on that generation, and so unfortunately we're wasting the output from that generation, or we have to we export that to the UK mainland when we can. So despite this success, Orkney is still heavily reliant, as the rest of the UK, on fossil fuels. So about 80% of the energy we use in Orkney still comes from fossil fuels, and that's why we're looking to tackle the transport and heat sectors. So just a little bit more detail on the Reflex project. The background schematic here just shows how we're looking to connect everything together. So it's basically a control and data collection schematic. The idea is that we'll largely use existing grid infrastructure, but we'll connect basically generation, storage, and demand together digitally. So we'll have either direct control, or at least we'll have data coming from the operation of those devices, so that we can hopefully match generation more closely to demand with the energy storage, and therefore maximise the use of locally produced renewable generation, and put this into basically our heat assets and our transport assets. To deliver this, we've set up a local company. So this is just a structure of how we're proposing to do things. So that local company will focus on the core activities here, so in the centre of that circle. So it's really about providing local customer service, developing products and services for the local community, looking at how we use the data from devices, and then ideally come up with IP, basically a toolbox that we can take that learning from Orkney and apply it elsewhere. And we're looking to work across what we call these 5 layers, so behaviour, commercial, physical, data, and remote control, and work with partners to deliver those technologies. So in some cases, we would look to deliver the technologies ourselves directly. In other cases, we would look to work with partners to deliver those technologies. Key part of the project is just understanding how we as humans interact with those technologies. So it's built around sort of the behavior side of things. So we're looking to deploy a range of technologies, as indicated on the left-hand side here. And we're looking to provide tools for local people. So if you go on the website, Reflex Orkney, you'll see that we've got, for example, a carbon calculator on there. So that's a freely available tool that people can use to basically estimate their carbon footprint. And then as they use the technologies, hopefully they can see the improvement in their carbon footprint over time. There's a whole piece around collecting information and data. The electric vehicles, for example, that we're rolling out as part of the project, they will have information coming back from them, which will allow us to see in real time the state of charge of the battery and where the vehicles are located on the network. So we can track all that. Okay, let's just look at a local level, just bringing all that together. Appreciate Gareth showed you this slide yesterday, but just looking at the if you like, the players, the key players in the UK electricity industry. Just to quick recap, the regulator is effectively under the sort of government control, so that's still a sort of public role. The rest of the industry is in the private sector. So that the system operator, Duncan and Craig will talk more about that, and the transmission owners are basically, and the distribution network operators. So where we've got networks, they're natural monopolies. They are the regulated part of the business, and then we've got generators and suppliers. These are the sort of non-regulated, more competitive parts of the sector. And increasingly, we get more and more aggregators. So companies such as Reflex that are looking to basically work across supply and demand. So I'll come on to codes and standards, and codes and standards are becoming more and more important, I think, certainly for the UK, in that as we've got more players, more participants in the market, it's increasingly important that we have well-defined codes and standards that they can work to. So whilst they're not new in any power system, they're obviously fundamental for a reliable and integrated power system. In the UK, they have played, I guess, an increasingly important role in making sure that a power system with a lot of participants is coordinated and working to the same set of rules. So really there to protect, obviously, people, assets, plant and equipment, and to promote the efficient and coordinated and economical development of the electricity system. I'm just going to touch on three of the main ones in the UK. So the quality of service guarantee standards. I've got a slide on that, and that's really aimed at the customer, so the consumer connected to the network. The security and quality of supply standards is really aimed at the sort of the overall design and operation of our transmission network. And then the grid code is really aimed at people that want to use the grid, use the transmission network. So that's largely aimed at big consumers, but mainly generators that want to connect to that. So they're generally put together and managed and reviewed by industry. So it's very much an industry-led process in the UK. So it's collaboration and consultation. But Ofgem, the regulator, generally have the sort of final say on decisions in the interest of the consumer and the wider industry. In some cases, special cases, Ofgem can allow parties to deviate, so move away from those codes or standards, providing what we call a derogation. So just looking at the quality of service guarantee standards, these are set by Ofgem mainly for the protection of domestic customers, although other customers do get the benefit of those. So small businesses and such like would get the benefit of these. And really it prescribes what the distribution network operators, so this is down at the lower voltage levels on the network, so the companies that are connected direct to customers, most of the customers on the network the level of service that they must provide. And if they don't provide that level of service, then they're required to make payments to the operator. So there's 12 service levels altogether within these. But just to give you an example, that if there's a failure to restore a supply, so say a supply is off, and this isn't extreme weather related, but if the supply is off for more than 12 days, so more than 12 hours, so half a day, then the customer's entitled to a payment of around, I think it's £75, which, just to put that into context, is probably around about 75% of the average take-home pay of a UK worker. So it's a reasonable sum of compensation. If they don't plan maintenance, so they don't give notice of maintenance on the network, then there's a payment of £30, which is around about 30% of the average UK take-home pay. And if they don't sort out things like voltage problems within certain times, then there's payments then. So these were introduced about 20 years ago to really provide the incentive framework for the distribution companies to make sure really they maintain the network, they're making sure they've got enough spares in stock to be able to repair the network quickly if there is a problem. As you'll see there, that's actually power cuts across the distribution system have fallen by 50% over that time. And the length of those power cuts, so when the power is off, it's decreased by 60%. So it has had a significant impact in terms of the quality of the service that customers are receiving. Next slide is the security and quality of supply standards. As I mentioned, this is really targeted at the transmission companies, or really for the transmission companies. So it covers both onshore and offshore, and it sets out what they must do in both planning the development of the network and also how they operate it. It covers generation, demand, both generation and demand connection criteria. And it sets operational limits, things like voltage limits on the network and things. The design part covers what we call the main interconnected transmission system in the UK, which is really the onshore network across the UK. The offshore transmission system is generally done by third parties, not always, but generally done by third parties. And most of those connections would be specific to generation sources, such as offshore wind farms. And it also covers both the AC circuits that we have and the DC circuits. And just some examples there of sort of typical requirements that they're required to meet. Final slide, grid code. As I mentioned, this is really aimed at the users of the grid in the UK, and it's really the technical detail that those users need to work to. So it governs the relationship between the users and the transmission owners and operators. And the document itself extends to over 1,000 pages. So it's really intended to permit basically an efficient, coordinated and economical transmission system, help with competition in generation and supply. So there's a common rule book for all those generators and suppliers of electricity, and to promote the security and efficiency of the overall system. It's broken down into 7 main sections, but those are some of the main sections within that, and in terms of how it works. So right through from how we plan things at the development stage, through to then how data is handled. Okay, that's me. So thanks very much for listening. Hopefully that was helpful, and I'm happy to take any questions.
Perfect. Thanks very much, John. Mas Kevin, could you pull up the poll, please, after this slide is completed? Thank you. To all participants, I would be grateful if you could participate in these few questions. And in the meantime, can I remind you as well to fill in your attendance form, as it is part of the certificate distribution after the 3 days. So whilst we are filling in these 3 questions, if I have any questions for John or comment, I'll take that now. And if you could just either make yourself known and speak directly, both in Bahasa Indonesia or in English, or through the chat box. I'd be happy to take Any comments or questions? Going through the polls now, it is 14%, 16% of you have voted just now. The first question is around the main factor that that determines the choice of an energy system. So it's a multiple choice and people can choose more than one. It's very good to see the variety of answers coming through. The second question is around the code and standards that are applicable in Indonesia as well as in the UK. So most of you have answered grid code at the moment as the main commonality between UK and Indonesia. And the third is around service quality, guaranteed service quality question. And most of you agrees to the statement as things stand at the moment. We are running behind schedule. So let me give a few minutes maybe for the polls questions to come in. Again, if the time doesn't permit for us to go through all of your questions or comments, we are planning on capturing all of that into an offline document and circulate them back to everybody so that everybody gets a chance to see the answers that each individual of you asks regardless. Okay, can I now, oh, hold on, I might have something here. There's a question for John. When renewable energy is integrated to the electricity grid for the first time, is there anything that needs to be modified on the grid code or practices? Would you mind giving a brief answer to that, maybe, John?
Yeah, yeah. I think if it's a new project that's coming on to the network, it would need to comply with the grid code. So we wouldn't normally expect to change the grid code if that's what's considered. Generally, changes are done through consultation. So all users of that grid code would be consulted before any major changes are made, and final approval I think is made by Ofgem.
Good stuff. Thanks very much for that clarification, John. Okay, Mas Kevin, could you please close the poll? And everybody could see the spread of answers and thoughts and opinions that people have around these three questions. Again, the main factor that is relevant or the main contributing factor in choosing an energy system, most of you decide that it's the resources that are available is the main contributing factor, and it's followed through by costs. The second question around code and standard, it's consistent with the development throughout the polling time that grid code is what most of you identify as being applicable in the UK as well as in Indonesia, and 99% of you agrees around the standard, and a standard for quality of service, guaranteed quality of service, is that it is something that the distribution company needs to fulfill, and if they're not according to the standard, then they are obliged to pay some sort of compensation. Thank you for participating in that particular poll, and let's move on to the next topic. Thank you, Kevin. So the next topic will be delivered by Duncan and Craig. And next slide, please. And both will cover certain issues, including the UK grid, electricity network, and integrity reliability, but also maybe share a little bit about the experience surrounding the blackout and outage management that we've experienced here in the UK. So again, for any questions and comments, please put them through the chat boxes or through the discussion sessions that we'll have after the topic is provided. Happy to take as much as we can during the time, but we'll be able to get back to you once this is collated and the session's concluded as well. Okay, over to you, Duncan and Craig.
Thank you, Nia. Very good afternoon to everybody, and thank you very much for your attention whilst Craig and I walk you through the first topic of our presentation today. So firstly, if we could have the next slide. Excellent. We will cover the integrity and reliability of the system. Myself, Duncan, I'll talk you through the first section of that, and then Craig is going to cover the second section, and then we'll switch around for the second half of the presentation. Okay, so we could have the next slide, please. John's touched on some of the background for this already, but I'll give you a short description of the UK grid system and then talk you through some of the aspects as to how that is managed in terms of reliability and integrity. So the British grid system is a winter peaking system. We are not so lucky to have such good weather as you have in Indonesia. It peaks on a winter evening at 5 o'clock when it's cold and dark. And you can see there it peaks at around 50 gigawatts supply. And then in the summer, the demand generally is lower because the weather is warmer and it's lighter. And summer peak is generally around 60% of the winter peak. Although in the major cities such as London, we do see high air conditioning load, and therefore for London itself, the summer peak and the winter peak are almost the same at around 5 gigawatts each. Okay, next slide, please. Brilliant. So that summer versus winter peak differential causes a number of criteria around how the system is designed. For example, most of the outages on the grid are taken during the summer months when demand is lower, and the same for generation and supply arrangements. The grid in the UK is operated to 50 hertz frequency, plus or minus 1%. And in terms of network reliability, the system is planned to N-2, so that it would remain secure for all supplies for a planned maintenance and then a fault outage loss, so for 2 events. And during operational timescales, it is continually planned to N-1, such that demand is secure for the first fault. Typically, in terms of voltage variation, we plan to plus or minus 5% voltage variation for a double circuit, though it can go greater than that. And obviously, the power flow on the system is continually managed within system ratings. There is universal use right across the system of short-term ratings for 10 minutes, 20 minutes, up to 6 hours, where you can overload the system for short periods to handle a fault. And we have meteorological enhancements to allow for hotter or colder weather, which would allow for more cooling on all of the key circuits and cables on the system. And the system has run like that for the last 50, 60 years. Increasingly, alongside voltage and megawatt thermal limits, we are seeing issues with grid inertia, with transient voltage issues during system faults, and with subsynchronous resonance and harmonics. And those new issues, inertia, transients, and harmonics, are arising because of the increase in non-synchronous generation, mainly from wind and solar and interconnectors. Okay, next slide, please. We transparently report the performance of the system each year, so you can find this on the web. The reliability of the system generally is very high against global comparisons. A lot of that is due to the fact that the British grid is a very densely populated area, particularly in the southeast of England, and that high meshed network means that often there is an alternative path for a number of faults. So the reliability of the grid operates at 99.99999%. And the vast majority of any loss of supply we see and any of the risks that we secure are due to weather and exceptional storms. And then typically when we see those losses, they are very minor, normally restored within either reclose time, so within say a minute and a half, or a short period after that, say within 15 minutes. And generally those losses are very, very small. So less than typically 50 to 300 megawatts for an instantaneous, very short period. The one significant outage that we've had recently, which affects reliability, is the 2019 power cut triggered by automatic protection relays triggering on low frequency. And we'll talk a little bit about that at the end of the session. Okay, next slide, please. To give you a feel for how the loading on the system varies and how we think about the operation of the grid, really many of the variations day to day are driven by the weather conditions in the United Kingdom. So for example, if we see a 1 degree fall in temperature, that is about 500 megawatts, half a gigawatt additional output, so or one thermal unit. For heavy cloud cover over the UK, that would increase demand due to lighting and reduced solar by around 1.5 gigawatts, 3 thermal units. From no rain to heavy rain is around 1 gigawatt. And then you can see all the way through there these different effects. The most significant ones we see recently are now due to variation in output of highly distributed and embedded wind, which is a 2 gigawatt swing. And then for big changes in solar PV output, which is all distribution connected, if you see a big change in illumination from the sun from one day to the next, and that could be up to a 6 gigawatt variation. Okay, next slide, please. So you can see those environmental conditions really drive the performance of the grid and how it is optimized day to day. Now we routinely see the renewable output on the system varying between 5 and 50% of demand. And that's fine. You know, we can manage that, no problem at all. The main measures that we use to manage that at the moment, we'll touch on in the next topic in more detail, but we have developed obviously high accuracy forecasting for both wind and solar and for demand. And the accuracy of that is under 5% error at 24 hours ahead. We still keep high flexibility from gas CCGTs, but we also use pump storage and interconnectors. And there's rapidly increasing use of grid scale batteries. And we're just beginning to see greater use of flexibility from EV charging, which is, we think in the future will be one of the most important sources of flexibility on the grid. And alongside those changes due to growth in renewables, we're already doing some adaptation for climate change risk in terms of the assets to maintain reliability. That includes increased flood risk prevention. Oops, we didn't need to go backwards. But increased flood prevention during and flood risk management due to high rain and much heavier intense rainfall. We are seeing greater dry spells as well during the summer, and that leads to greater risk, greater likelihood of ground movement and subsidence as the water table changes. And there's a number of remediations and developments that we've made to reduce that risk. We are seeing increased cooling requirements on the assets during regular operation because of higher temperatures in the summer. And on coastal sites, obviously many of the infrastructure key asset points are on the coast. We've got higher risk of erosion and of course increased intensity of storms in some areas, so we have mitigations for that. Okay, next slide please. We can, here we go. So that's, I've given you a picture of the network and the assets there. And then I wanted also to give you a picture of the people and the processes that are operating that. The people and the processes are as important as the...
Sorry, Duncan. Kevin, can you check there's some background noise to Duncan's presentation?
I think Craig did. There's noise from Craig or Duncan. No.
Okay,
you could try it again.
Thank you.
Try to unmute again.
Thanks, Nia. We'll just try that there and see how it goes, yeah? Can you hear me now?
Yes, please. Yes, that you're loud and clear, Duncan.
Brilliant. So in terms of the people and the organization, there is now a significant long-term planning activity going out over 30 years, which involves a very wide industry engagement, many organizations, hundreds of organizations. I can hear that again. And thousands of people extending scenarios out to 2050. And then we do detailed.
We still have the leaks, Kevin.
Okay. Try again, Duncan. I think there's some feedback from your side, but you can try again now.
Yeah, okay. And then detailed scenario and power system modeling occurs out to at least 2035, obviously where we're looking at investment in assets, and the investment horizon is typically 10 years for a major asset. So obviously the detailed modeling goes out significantly further than that. Then within the 10-year window, we're really then into detailed system connection, design and construction. And because there is so much construction on the grid, there's also a very detailed maintenance plan going out at least 5 years, because obviously outages for maintenance need to overlap with outages for construction. And that involves around 250 people. Within that process, there's extensive modeling of the growth in renewables and the change in the technical performance of the power grid. That's an incredibly complex process with hundreds of different factors. So we've established a management principle based on Toyota's lean principles, and we have an ABEA program plan, which is again a Toyota management principle in order to run that. And there's very wide industry engagement and commercial market analysis of that evolution and of the network plan. And then from 1 year ahead to real time, we're into continuous remodeling and operation. It's around 300 people involved in that, including the control room. And that's a continual plan review week by week out to 1 year ahead, with financial incentives on the organization to minimize that cost of operation and to contain the risk of supply. So overall, you've got around 600 people there, if that's just the next slide. The ESO, sorry, you can go to the next slide, thank you. You got that perfect. The system operator is structured with an independent board and an executive team. And then within the organization, the activity is split by strategy, which is long-term strategy, modeling and innovation. Engineering, which deals with all of the network and technical performance characteristics of the grid, connection and contracts. The commercial and markets team, which are looking at all of the commercial modeling, long-term contracts and short-term contracts for balancing and operation. And then the real-time operations team, which includes all of the real-time activity and the supervision of all of the IT and processes to support that. Total staff across the system operator is around 800 personnel, excluding the IT. And then there are around 300 committed IT staff purely working on system operator projects, although that does move up and down by plus or minus 100 based on what's going on. We're also very proud of the fact it's a diverse team. So the executive team and the board are 50-50 male-female. It's a very international team. We have over 35 nationalities across the team, probably more than that at the moment. And over 200 chartered engineers within those 800 personnel. So again, it has a strong engineering focus and actually a strong commercial focus as well. Okay, I've got one final slide. Brilliant to pass on to, at that point, I'll pass on to Craig Dyke, who will talk you through the 9th of August power cut. Craig, over to you, if we can switch over.
Yeah, thank you, Duncan. I'm hoping I'm coming through loud and clear. Good morning, everybody.
You are.
Or good afternoon, I guess, in Indonesia. Thank you. So next couple of slides are just to talk through the power outage that the UK saw on the 9th of August 2019. So just a couple of slides. Walk me through to the next slide, please. So just to paint the picture, so it was 9th of August in the UK, sort of, I guess, close of play 16:52, so people leaving the offices, heading home. School summer holidays, so people are probably heading off, packing up, ready to go away on their summer holidays. But to Duncan's point, it was a typical British summer, so a little bit of abnormal, not much sun, a little bit of lightning and thunder across the UK, but weather conditions are anticipated, yellow warnings issued by the Met Office. And from a system setup perspective, we had a good balance and mix across the generation market provided, and also the right tools and processes in place. So overall, the system in itself and the market were in a good position. Series of lightning strikes across various parts of the network, and typically across the UK, we may see over 1,000 lightning strikes across the whole UK at any one with an annual period. It struck a key north-south circuit running down the east side. Typically then the circuit tripped, as you would expect, within a few milliseconds, and then restored itself within 20 seconds. So actually from that point in time, the lightning actually tripped the circuit. It detected that the fault was lightning, therefore the circuit being restored, and actually at that moment in time, everything will look like it should have been. So everything was absolutely fine. Coincidence of the lightning strike, there was a trip of 500 megawatts of embedded generation, and that's generation sat at the distribution level below the transmission level. So that's typical, we'd expect to see that. So at that moment in time, lightning strike, tripped the circuit restored. Everyone in the control room thinks, right, normal operation. However, immediately following the lightning strike, we saw the tripping of two key generating points. So Little Barford is a gas-fired power station. We saw its steam turbine trip off at that moment, coincidence with the lightning strike. In parallel, a wind farm known as Hornsey, which has been referenced in earlier presentations, that also tripped off the network as well. So when you add up the embedded generation, Little Barford gas-fired power station, the steam turbine, and Hornsey, we saw over 1,300 megawatts of generation trip off, coincidence, at the same time, which was greater than the largest loss recovering on the day. What that meant for us was that we saw the generation fall to 49.1 hertz. So back to Duncan's point, the statutory limits of 49.5 to 50.5 hertz, we dropped down to 49.1 hertz. Frequency response kicked in, and we saw the actual frequency return and restore back up towards 50 hertz. As it started to recover, we then saw subsequent trips at Little Barford of another steam turbine that actually tripped off, and then another gas turbine also tripped off as well. And what that meant was we saw the frequency drop to 48.8 hertz, which triggered low frequency demand disconnection. And that's demand at the distribution level that is actually has to come off the system when the frequency drops that low to actually restore the frequency back up to 50 hertz. In parallel with this, then the control room had taken over 1,200 megawatts of manual action to actually restore that frequency back up. And the 50 hertz frequency was restored by 16:57. So from that 16:52 through to 16:57, there's 5 minutes of activity that actually saw us restore the frequency back up to 50 hertz. At 17:06, the DNO started then began connecting customers. So reconnected the customers. By 17:37, all supplies returned to all customers. That's 45 minutes of activity from a simple lightning strike, which would be standard, through to generation tripping off, the frequency falling, demand being disconnected, and then restoring all demand. So all that within a 45-minute window. However, in parallel with that, there were some other issues going on that were outside of what we suspect on the system, which were found in the following investigation. So there were train lines within London, which were subsequently found that incorrect settings, and they actually tripped off and were stuck on the line. It required manual intervention to restart them. So that caused a lot of backup and people issues within London. Clearly, this is rush hour. This is 700 hours on a Friday. People coming into London, people leaving London, and that saw a lot of press and actual people getting stuck in there at that moment in time. And there are also some issues as well we found out through the investigation, whereby there were some buildings, such as a hospital, for example, that was on the wrong set. It shouldn't have been on the low frequency demand disconnection. So you just move on to the next slide. It just shows this all pictorially as a frequency response trace. Coming through now, thank you. So what this actually shows, starting on the left-hand side, so the blue line through the middle of the chart actually shows a frequency trace. So typically we were sat at 50 hertz at that moment in time when the first lightning strike actually occurred. You can then see that frequency trace start to fall. On the left-hand side, so it falls down to 49.1 hertz. The frequency response, which the control room have already sat, they've already instructed, is sat there to automatically react, then starts to bring that frequency back up, and it hits 49.2 hertz. We then see a gas turbine little Barford then trip, which then sees a further fall, coincidence with what we found out through the investigation, that there was an additional 200 megawatts of generation that also tripped at 49 hertz. The frequency then falls to 48.8 hertz, at which point the low frequency demand disconnection then starts to kick in. Then that starts to arrest that frequency, which then drives back up. Again, as the frequency starts to return, we then see the final gas turbine trip at Little Barford, which then there's a little bit of a dip in frequency before actually see that frequency trace start to restore and work its way back up through the automatic frequency control, but also the actions to restore frequency that the control room actually took. And that was using your typical gas turbines, interconnection, hydro, and also storage as well through batteries. And back to 1657 is where we saw the frequency restored back up to 50 hertz. This all happened in a very short space of time. It triggered a significant investigation into what happened on the day. It led to National Grid's Electricity System Operator needing to write an interim report and then a final report, and then Ofgem leading their own investigation with UK government as well. Because this was much broader than just the electricity system. It was also trying to understand what was happening at distribution level. So the distribution network operators were also involved as part of the investigation, as were the generators involved in the tripping as well. And it led to some key actions as well. So it's leading to some grid code changes. It's also leading to National Grid, as the electricity system operator, running a quite extensive program to actually go out and actually change some of these relay settings on generators embedded within the distribution networks. So from what seemed like a very innocuous lightning strike, typically, as we said at the start, 1,000 you've seen per year, led into some significant major industrial change, industry change. But at the same time, recognizing that these were all faults that occurred coincident with each other that were all actually independent. So that was the 9th of August, 2019, and that was the power outage on that day. Next slide. I think that concludes this part of the presentation, I believe. Next slide, please. Yes, I think we should now be okay for Q&A. I mean, if people want to know more into this, there is at the bottom, there's a link to the August the 9th report page, which sets out the interim investigation, but also the final investigation into what happened on the 9th of August as well.
That's perfect. Thanks so much, Duncan and Craig. Can I maybe ask Mas Kevin to pull up the polls, please, whilst we go through some of the comments and the questions that's been already posted on the chat box, and I see Duncan have responded as well to one of them. So yes, if I could ask people to start filling in the polls whilst I go into the questions that have been captured. So around the forecasting, that's great. Duncan has responded directly to that. If everybody's interested, it's on the chat box, which will be circulated as well. And definitely between the British Embassy and Mentari team, I think we are definitely planning a dedicated session for a workshop. If one of those dedicated workshop will be around forecasting, that is a good, a recurring theme, I think, that's been presented throughout the different interactions with the Indonesian government as well as PLN in January. So we've taken a note on that. The second one that have come up in the chat box earlier was a question on the electricity tariff per kilowatt hour in the UK. Could Craig or Duncan perhaps respond to that? What is the electricity tariff per kilowatt hour in the UK? That is a general interest question, I believe.
Yes, sure. Craig, should I do that one?
Yeah, well, yeah.
Yeah. So yeah, generally typically the tariff at retail for home use is around 13 pence a kilowatt hour, something of that order. It's about halfway through quite a delayed smart metering program in the UK, And I think in 2023, we have half-hourly settlement coming into the UK, at which point users will be able to be much more flexible about when they take power. So we have some trial smart tariffs at the moment, which could allow you to get down as maybe as low as 5 or 10p a kilowatt hour, but typically retail is around 13 pence. Of that 13 pence a kilowatt hour, around 4% of that cost goes to transmission, both for operation and for construction of the assets. And I think, Craig, around 15%, and maybe a little bit more is distribution, maybe 20%.
Yeah, 20, yeah.
Yeah, about 20% for distribution.
Okay, thank you very much for that comprehensive answer. Both the second that I have come up as well is around the indicators that the UK use to know the reliability of power supply. So what indicators does the UK use to know the reliability of power supply?
Craig, should we do a team answer on this one? I think at a high level, as Craig's just shown, for a start, any incident on the grid is reportable to government. We have a formal process to do that, and for a significant incident, obviously, we provide a more detailed report. And we also have to report to government any variation outside of limits in terms of voltage or other system characteristics as well. Craig, do you want to talk a little bit about the planning process and some of the criteria we use in advance?
Yeah, so we generally look at the network right from many years out, right down through to day ahead to 1 hour ahead. That's the general process regards how we model the network. When we model the network, we go back and we use the, I think I referenced earlier on, the N-2, so the loss of 2 coincident circuits on the network. And we also look at if there's also already a circuit out on the network, what we then typically call N-3, so an outage followed by 2 subsequent trips on the network. And that is carried out right from many years out, right down through that hour ahead. So, and we are looking at that prevailing network conditions, so what the network looks like, any activity on the network from a construction perspective, outage planning perspective. We're then rolling a lane on top of that, then what the demand looks like, whether it's a winter demand or summer demand, and then typically at what point in day as well. So whether it's overnight, middle of the day, or the peak, for example, in winter. You're then looking as well different generation backgrounds as well. So what you expect the market to present to you on the day. So typically what you might expect in winter or what you might expect in the summer on a hot day, cold day, sunny day, overcast day. But then you're also stretching the network. You're also stressing it. So you're also saying, well, actually, what happens if? There's a lot of scenario planning goes into that as well. And then the accumulation of all that then allows us then to plan each day and then operate the system on a day-to-day basis. Regarding the network reliability, that gives us real confidence as we go into any typical day, any typical hour, that we can control and operate the network. If we pretend with whatever prevailing conditions that we expect. Post any day, then we will undertake the analysis as we presented from the August 9th. We would look at the performance of the network from a was the asset there? Did it perform as expected? And there's accumulation of all that data then drives that 99.9999% high reliability of the network. So it's starting right out from years ahead, right down through our ahead, and then post day as well. It's that looking back, and that then drives us that confidence that we can actually operate the network, and we have then gives that high reliability of the network as well.
Great stuff. Thanks brilliant. Thank you.
Very comment. And Nia, I think just to add to that, I put a little comment in there. We also work very closely with each of the networks to understand whether there are any specific performance issues due to the assets. So historically, there have been systematic issues around things such as transformer cooling, reliability of certain current transformers, voltage transformers, and also particular cable insulation technology. And when we have a known incident like that, obviously there will be enhanced monitoring and maybe even enhanced security arrangements around those assets, such as a risk of trip, so that you're more prepared for that. And I would say, Craig, probably once every 5 years, we see a major asset issue, which then requires a complete replan of the maintenance schedule and everything else in order to quickly fix that problem. Because we always worry about a reliability decline where if you have if you have increasing unreliability, it makes it much harder to plan. And if you can't plan, then you tend to get increased unreliability in the future. So you can get into a vicious circle.
Absolutely. No,
we could go on all day on that, Nia.
Yeah.
Sorry.
No, thanks very much, Duncan and Craig, because I think it's important to give that broader context so that, tackling a certain issue doesn't mean that you only, fix the quick fix solution or identify the one specific issue, but actually understanding how it ties into the rest, either pre the situation, planning ahead, and also dealing with what's coming at the moment, and then going back and fit the learning back. So I think that brings everybody into that same space, because we, as you know, the participants come from a different range of backgrounds, some in the planning department, some in the quality control, some in the operations. So I think your combined answers would benefit everybody in this space. Thank you for that. And I think we still have time. So before I go and read the poll results, there is one question actually that is related to around blackout resilience, or including blackout resilience. So in relation to what Craig has presented around the blackout management, a while back, we had this discussion with some of the colleagues in the ministry. There are recurring issues and questions around, is there actually, in the UK case, is there a practical, legal, or fiscal arrangements for these special access transmission customers with specific regards to supply quality, stability, reliability, and including if such an event happens, such as a blackout, how do you deal with this special access transmission customers? Or does the UK have special access transmission customers?
No, generally it doesn't, Craig. So we have public safety provisions around, for example, chemical and large industrial sites, where if there was a shutdown, then it would be very dangerous and pose a threat to the public. And for that, the responsibility for their security of supply rests solely with the site, not with the network. So they must have their own provisions for backup power and for system security as well. On the transmission system as a whole, we have a single standard for harmonics and a single standard for black start, and there is no prioritization other than the total restoration of the network within that. There is not even special arrangements for the capital city or for the centre of government or anything else within those black start arrangements. The only special measures that we do have are associated with the safety and security of nuclear power stations, for the obvious reason that they need, as part of their nuclear license, they need to ensure that they have specific arrangements around the network, and that we have put additional tests into the performance of the system for things such as voltage and harmonics. But they are effectively enhanced risk management. They don't actually have any additional improved performance of the network around reliability or harmonics or anything else. So no special measures, and any special measures must be managed locally by the site.
Okay, thanks for that. That's a very clear answer from you. Hopefully that addresses some of this issues that were raised by colleagues in ESDM. Okay, I think we can safely close the poll. Kevin, can I have and display the results, please? This is a question around whether anybody is responsible to manage a team in your department. So 68% of you answer that you do. And the second question is around what would you think influence the integrity and reliability of electricity network. Most of you think that it is the technical factor. 80% of you actually choose that, and quickly followed through by management. Sorry, and on the skills of the individuals and groups that operates them is at 43%. The third question is around COP26, because we have COP26 team here. People think and have put forward their thoughts on that. The next one, which is coming, is to be undertaken in Glasgow. And some of us actually think it will be in London and in Orkney. That
Orkney
is,
would be great.
it's a good point. I know. Okay, that's great. I think. Absolutely. Okay, so I think we're just, or if not a little bit, on time. Do we have about a minute or two to go over, or are we ahead, or are we early? How are we on time, Henny?
You're ahead.
Eddie, I'll take one more question actually, because we are early. So how many number of private and national company involved in a whole power grid system in England, and where is the position of English National Power Company takes place, especially in relation with customers? Shall I repeat that question? Or
No, that's fine. It's a great question. I think Craig's nodding as well. So I think as John said earlier, I mean, 30 years ago, there were really 10, 15 organizations involved in everything, in the whole supply of electricity in the UK. Now there are hundreds of companies involved in it. I think, Craig, do you want to start? Maybe you start on the network and retail side, and then I'll pick up on some of the broader bits.
Yes, I guess from a straight network perspective, clearly you've got the three key transmission owners of National Grid in England and Wales, and then Scottish Power and Scottish Hydro Transmission in Scotland. And so as the transmission network owners, so below that, you then have the distribution network owners, and I think typically there are 14 licenses, albeit I think it works out at about 6 actual companies that operate at distribution level, give or take. When it comes into the market, at Duncan's point, if you went back 5-10 years ago in the UK, people would traditionally talk about the big 6. So your RWEs, your Eons, typically making up the bulk of the market. And that doesn't get talked about anymore. And that completely changes with regards how the market presents itself. So we saw that transition to a lot more independent generators coming along, but also newer technologies as well, such as storage and aggregators entering the market. And then when you look at aggregators themselves, whilst it might be a single unit, that actually is then broken down into multiple sites, whether that's generation sites or actual demand sites. So that whole makeup of the actual system physically has changed consistently over time. So physically, it's still the same network, but the number of players and participants is increasing significantly over the last decade, if not beyond. When it comes then down to the supply side, again, typically you would have seen the big suppliers supplying us at domestic level or retail level. And that, again, has changed significantly. You see a lot more small suppliers, and some will come and they will last for a long time. Others will sort of come and go. And you see a lot of that, certainly through the winter with price spikes. But you then see some other new suppliers come along, completely from left field, completely turning how they supply and provide tariffs to customers. So the likes of in the UK, we have a supplier, they're called Octopus, who come in with some real innovative ideas around tariffs. So tying in tariffs at a domestic level through to the amount of renewable generation on the network, and also that linking it to wholesale price. And what that does, it brings the consumer, us as individuals, into play. It makes us a lot more conscious, and it makes us actually drive decisions based on what the market's doing today, not what we think we may want to spend in 3 or 4 or 5 months' time.
Brilliant. And I think, and as Craig says, a number of those companies are less than 10 years old. So they've really only been created really since renewables started to go onto the grid. I think overall, I would say that there are probably now, I would guess there are probably more than 40 companies worth more than £1 billion active in the UK energy sector across everything from planning and development through to delivery of construction offshore and offshore wind, through to supply and retail. In retail, there are probably 5 or 6 large companies still doing retail to domestic consumers, and then maybe another 25 or 30 small companies, either involved in a particular region or to a particular type of customer, say the elderly, or those with a green tariff or similar. We're also seeing, we're expecting to see the arrival of banks and the banking sector into energy, but as they start to fund energy efficiency and some investment in things such as domestic solar and heating, we're expecting them to come into the market as part of the next set of green measures that will come in the UK. So that will add a different strand.
Great. Okay. Thank you both for that answer. I think
Yeah.
we can go to the next topic, and I saw a question that probably will be answered in some of the slides, or we could discuss it a bit more afterwards if we need to. Tim Bahasa Global, could you please pull up the next slide, please? So this next topic will still be with Duncan and Craig. And if you could move on to the next slide, please. And we'll see how the UK grid renewable energy integration issues have been undertaken and assessed and dealt with, and also some specific issues around moving from synchronous controllable generation to asynchronous. And then there's some areas for discussions around the low inertia solutions and new markets, and also touching on a little bit on the developing smart local energy systems. So I'll just at this point hand over to you, Duncan or Craig, who's
to
starting?
Craig. Yeah, to Craig.
Yeah, Craig. Yeah.
Good stuff.
Okay, so the next stage, as we sort of just spoke through, can I have the first slide, please? And you'll hear a lot of repetition as we go through this, and I think that's quite important, because I think for us to get across the UK experience, I think that's repeating and showing how it all joined together is quite important a message to get across. Just move on to the next thing. So I can just talk through what we're going to look at. So when you talk about the UK journey, what's happened over the last sort of 10 or 15 years with this transition to renewable energy, but also have the integration issues as well. So there's a lot of things which we anticipated and we got right, and we've also undertaken a lot of learning as well as we've gone through. So we will talk through some of that. We'll then move on to some other specific issues. So as you drive towards integrating more renewable energy into the network, what are some of the issues that you might come across, but also then what are some of the solutions that we actually are undertaking within the UK that actually will help us integrate more renewable energy as we move and drive towards net zero. Just move on to the next slide, please. So we've already seen a lot of graphs over the last sort of day or two regarding that drive towards renewable energy, so in particular wind, so typically 40, 50 gigawatts. There's a big drive in the UK at the minute for 40 gigawatts of offshore wind by 2030, which requires a significant development, not just in actually building out that offshore wind, but also in how it's built as well today. So a whole new coordinating regime has been developed alongside that. And also solar as well. So that drives was 10 to 20 gigawatts of solar, typically at embedded generation levels down the distribution network. That's a significant amount of growth in renewable energy against a backdrop of a peak demand of 50 to 60 gigawatts. So it's a hell of a lot of renewable energy at the same time against what is typically not a significant against demand side. So to facilitate this change, we talked about there's a need to invest in networks. Invest in networks ahead of need, so using anticipatory investment, but also using scenario planning as well. So typically in the UK, we develop what's known as the future energy scenarios, which are typically a look at how you can drive towards a net zero world and what some of the pathways that might actually happen, that might drive the actual need for the network, that might actually drive the need for the market, and also what businesses use as well to drive their own business plans. And we take that scenario plan as well to ensure that we stress test the network to ensure that on a least regrets basis, the network can stand up should any of those scenarios that the most likely to occur actually take place. From electricity system operator perspective, it's easy to think that, okay, we just let the renewable transition happen. It will happen, we'll drive towards net zero. But they've been ambitious enough to set themselves a target that by 2025, they'll have the ability to operate the network carbon-free. So if the market presents a carbon-free position, the electricity system operator will be able to operate that network carbon-free. And there's a lot of work going on in that space. That's the development of new markets, which we'll talk about towards the back end of this place, but also adjusting the existing markets as well to allow technologies that exist today into those into the markets and actually participate. So there isn't a limit on the penetration of renewables. This isn't an arbitrary limit. The technical and commercial solutions are in place, but you can always develop beyond that. And that's through interconnectors, storage, demand-side synthetic inertia, and typically as well, where we expect to see those big flexible loads available, not just to the electric system operator, but also to the market as well for heating, cooling, electric vehicles. Next slide, please. And this is important as well, is recognizing that this variability in renewable energy, because of the way the market in the UK is designed, the wholesale market is actually incentivized to ensure that risk around the renewable energy, that intermittency is actually removed from years out, right down to 1 hour ahead. So a lot of that is managed by the market. And the system operator function then manages those last half hours in the lead up to real time. And the flexibility today is driven by that high accuracy renewable forecasting, which we've already talked about. So ensuring that as we move down from day ahead, 12 hours ahead, 4 hours ahead, an hour ahead, that we have a really good understanding of what the market will present from a renewable energy perspective. The market incentives are there to ensure that each individual can balance their own position, and ensures that they cover their own position. The electricity system operator is there to manage that residual balancing element. And I've already spoken about as well around how we develop our ancillary services markets to facilitate new assets, facilitate demand side participation, battery storage, and any other new technology that might come along. And that isn't a new thing. We've consistently developed our ancillary services markets over time. This is now the need to develop them further as new technologies come into the marketplace, but also how consumers will react as well. So how consumers can play their role to drive towards this net zero position. Next slide, please. But we shouldn't forget about what exists today. So it's easy to look forward and start talking about the electric vehicles and storage and batteries and all that really nice stuff, and smart meters, all that real sexy stuff that people talk about. But we mustn't forget their exact assets that exist today that are really, really important for that transition. So the existing gas turbine, that's the development of flexibility within it. So typically, historically, they would have run on a one-shift basis. And that means they would typically run up and down one day within a 24-hour period. It's those actually adjusting their own generation assets on site, which allows them to ramp up, come onto the network, and come off twice within a typical 24-hour period. So that provides flexibility to the market, but it also provides flexibility to the electricity system operator as well. Interconnection. I know earlier on, I think John presented a list of all the key actors within the electricity market today, from transmission owners to generators to suppliers. For me, I think there was one that was probably missing off, and that's interconnectors. Interconnectors are significantly important to the UK because it's an island. We can actually manage the need for that flexibility, not just from a UK perspective, but using Europe and other countries as well. So it becomes a much bigger network. And that's a drive from 2.5 gigawatts to the anticipated strategy towards 10 gigawatts of interconnection for the UK. So that interconnection provides that carbon-free generation from the likes of Norway, for example, but also provides that flexibility. And that's either Europe providing it to the UK or UK providing it back to Europe. And we shouldn't forget as well, we've got existing pump storage facilities in the UK, where that we have in North Wales, we're in Scotland, and that provides that real dynamic reserve that we need to keep that frequency within 50 hertz. Energy efficiency. So this goes back 5 or 10 years. So that drive towards renewable energy, towards 2020 targets we have in the UK, start off with energy efficiency, whether that be insulation in the homes, and also, I guess, things like TVs, which drives that peak, and I guess change the light bulbs as well. So that drives that peak demand down. So it's not just about building generation assets up to an existing peak, it's making sure we can bring that peak load down. And energy efficiency has been a significant drive in the UK over the past decade and beyond. And recognizing as well, the ancillary services markets we have today are really mature, but there's still that need to development for more embedded generation, embedded demand, and also battery storage as well. Next slide, please. So where do we see this change come in? Again, apologies for repeating, but we do see that reduction in operation of the gas turbines, and that will be offset by that enhanced flexibility we're going to get from interconnectors, that growth of EVs as that drive towards the removal of petrol and diesel powered cars in the UK comes into place, that transition, that real ramp up towards electric vehicles being the car of choice. that could see us having significant opportunities there from a market perspective and consumer perspective for those flexibilities of moving that load around to match the actual generation. So traditionally, it's all about having a demand curve and making sure the generation matches demand. In a renewable energy world, that could see it flip the opposite way, whereby you're matching demand to generation. So it could be a significant change from where we have been over the last sort of decade and beyond. I'm recognizing as well in the UK that surprisingly, we do get those warm periods, so we will see more cooling demand on, which allows us to shift and play with some of that. But typically as well, the move towards, I guess, electric heating and the use of heat pumps as well, which allows us to flex that heating load, that cooling load to meet that generation. Again, we do significantly see and expect to see the electric vehicles providing that real rich source of demand that actually facilitate balance in the market, but also from a system operator perspective, which will facilitate that drive towards renewable energy and also that variability in energy that renewable energy provides. Next slide, please. But you shouldn't forget, I know we touched on this already, and I thought worth covering on some of the key points. So typically, I think this goes back 20 years when I first joined National Grid, we would typically look at each day, we typically carry out 2-3 studies on it, looking at each day of the year based upon the key cardinal points. So they're the key, either the trough of the day or the peak of the day. We're now moving away from that and looking at modeling the network across multiple points of the day because of the way demand's actually being used and the way renewable energy is actually presenting itself as part of the market. And what that means on a day-to-day and practical basis, there's a lot more data available to system operators in the market that actually allows them to understand what the network characteristics of the networks actually look like tomorrow. And with that becomes a need for much more powerful computers. So that computational burden that you'd expect to see is making sure that we have those right assets, those right computers in place ahead of it, so we can actually crunch those numbers, using that development of artificial intelligence and innovation to actually make sure that we better understand and better model the network characteristics. And it's also modeling things as well, which we may not have needed to in the past, because traditionally that move towards renewable energy drives the need for some of the gas turbines and coal-fired power stations we talked about to come off the network and come off the market. And that drives a need for us to better understand the inertial characteristics of the network, those voltage characteristics, the frequency stability, which we haven't had to in the past, but we will need to moving forward. And one of the key bits as well is recognizing there's that need for more data as well. So that intellectual property that comes along with any asset on the network is making sure that the system operator has the right access to that data so it can actually model the network and better understand what it means. So there's some code changes going on in the UK, which will oblige some of that intellectual property to be provided to the system operator, but on a needs-only basis. It can't be shared beyond that. Next slide, please. So I've already touched on this, recognizing that there's a significant investment in that data and modeling, and that's where we see that key elements. And we talked about earlier on, Duncan presented the key resources within the system operating 800 resources. The IT function, so that computer function which we have is 300 plus resources that also support the system operator as well. And that's maintaining the existing systems, but also developing those new systems as well, which we'll actually need to make sure we can operate the system as we have historically in the past. And there's also looking at new routes to gather data as well, whether that's contracts with aggregators, partnerships with universities and studies with them, and also getting volunteers at data hubs. And that's one of the big things as well. So that's that data and digitalization, recognizing a significant amount of data out there, probably more than we've ever realized, and actually making sure that the right people have got the right access to it so they can make the right decisions ahead of need, whether that's the system operator or the market or the network owners. And that's what will allow the public themselves and the business themselves to actually encourage that environmental and price-driven change in demand time. So that data and that ability to model it go hand in hand, and that's a significant change that we expect to see, not just in the next 5 years, but it's actually happening now. Next slide, please. So the next chart you'll just see on your screens now. It typically shows the activity that is undertaken within the balancing mechanism by the system operator. And you can see on the left-hand side, that first sort of quadrant is 2008-9 to the right-hand side, which is in the last year, which is 2009-20. You can see that blue graph just sort of move up, move up, move up, move up, move up. And that's because the system operator undertaking a far more actions in the market from a volume perspective to manage congestion, voltage optimization, inertia, and that increased variability from renewable energy. But that's not just because we are taking bigger actions, but because there are more market actors and market players within the market that present themselves. So it's not just that big six anymore. It's the demand, it's the storage, it's the aggregator. So it's undertaking a lot more smaller actions as well, which drives up that significant shift to the right-hand side from the left. We see that increase up to 65% of proportion of the market has been moved. Next slide, please. And this hasn't just happened by chance as well. So probably a decade or more ago, there's a big significant policy decision to facilitate that drive towards 2020. So the original target set by the UK government recognized that the way wind was connected to the GB network would facilitate hitting those targets on time. So it's recognizing in order to allowing wind to connect to the network ahead of that network being invested, and actually those upgrades in Scotland in particular, would cost. And if that's typically in the order of £150 million per annum, but actually on a cost benefit analysis, that is actually the right thing to do in order to hit those targets and obviously facilitate that drive towards the 2020 target and that drive towards net zero. And actually what you see then, that resolution, the upgrades come online. So we've had in the past 18 months, 2 years, a new DC link between Scotland into north of England on the west coast. Further developments on the east coast as well, which then facilitates that drive to get that renewable energy out of Scotland, which actually facilitates that. And it sets that blueprint, which we talked about, for that offshore, that growth in offshore wind. It's that 40 gigawatts of offshore wind we expect to connect by 2030, and then significant targets out to 2050 as well. And also we look at as well managing that inertial challenge as well by reducing the largest loss on the system as these new inertial services come online, whether that be driven through synthetic inertia or other means such as batteries, for example. Next slide, please. And again, it's important to recognize that this flexibility, and flexibility is the key word, won't just come from your additional generation sources. It will come from that drive and that shift in the makeup of the demand as well. So typically you see that chart on screen, which will drive from 2020 to 3 terawatt hours of EV heat pump demand to what we expect to see in 2025 at 11 terawatt hours. That's a 370% increase in energy for those two types of technology. But we expect new products and services to be driven, as we already see some of the real innovative solutions coming through in the retail market. They'll make sure that balancing becomes a lot more simpler for the market, and also there are more tools provided for the system operator as well. And that real drive towards recognizing the digitalization, so the expansion of IT, control and dispatch is really significant to grow the markets in these areas and have that dispatch capability. Next slide, please. And we've already talked about, I think one of the questions talked about Black Start. So Black Start is that typical service, it's our insurance policy. So should the unfortunate happen and the network actually shuts down, it's that ability to restart the network from nothing, right from the ground level. So typically a Black Start service would have been provided by your coal-fired power stations, sat there with a big piles of coal, can fire themselves up and get running within 2 hours typically. We're now seeing clearly with coal coming off, there's a need for system operator to look at new solutions for that. And that's looking at hydro, which we've typically used Black Start, but also into interconnectors as well. So using interconnectors to drive Black Start as a service. And also there's an innovation project in the UK as well, looking at distributed level generation as well. So information, so technology at the distribution level, building the network back up to transmission level. And also looking at running it in a very different way from a commercial perspective. So typically Black Start would have been bilateral contracts. So a contract between the system operator and the generator directly with no involvement from anyone else. In the past year, 18 months, the system has been running tenders. So running open tenders in parts of the network to test if there is competition, one, to drive the price down for the provision of Black Start service, but also to give those new market signals to new technology as well. And that's part of the whole UK Black Start strategy as well, which then drives that whole policy from a UK government perspective, ensure that we can get that network back up in the right areas at that right moment in time, should the inevitable or should the worst ever happen. I think that concludes my element. Let's go on to the next slide, and so I'll just now hand over to Duncan, who'll talk through aspects of the low inertia system.
Fantastic. Thanks, Craig. And hello again from me. And so I'm just going to close this section of the presentation by summarizing then the aspects of a low inertia system, which, as you can see, is very much where we're getting to in the UK. And just, Craig's walked through a quick high-level summary there of all of the measures and particular things that are changing on the UK grid, and which we hope are useful. It's a very different grid in Indonesia, vast and amazing country, but some of those principles we hope are useful. And over that period really that we're talking about, which is 2005, 2010 through to 2020, so a 10 to 15 year period, we have seen a complete translation from a large unit power system based mainly around coal, nuclear, and some gas, to a system now which is really, from a balancing point of view and a day-to-day operations point of view, really leaning heavily on batteries and distributed generation, with only one coal power station left now. And then we see, as Craig said, a continued decline in the use of gas over the next 10 years, and more interconnection and smart demand control with EVs. And underneath all of that big transition to small and distributed is a significant reduction in the inertia of the system as well. And that's really one of the big new parameters that we are dealing with. And as Craig says, we see there is no technical limit to the level of renewable generation or the level of non-synchronous generation that can be accommodated on a reliable, secure and economic power grid. We have a target in the UK to be able to operate the network reliably without any synchronous generation by 2025 regularly. And as Craig said, by the time we get to 2030, we are expecting that to be a very, very regular occurrence, and for a significant proportion, and indeed the majority of supply, to come from non-synchronous sources. So how do we achieve that in terms of inertia and as the new sort of security variable? So you can see in the charts here that inertia will, on average, inertia will decline from around 200 GVA, which is what you'd find on any typical system if you went to France, to the United States, Texas, India. You'd be looking at inertia systems around the 200 to, well, even much higher on a continental system, at 500 GVA type figures. The UK system at 50 gigawatt peak varies significantly during the day. So we peak in the afternoon in the winter at highest demand, and then some of those power stations come off overnight, and overnight we tend to sit around 150 to 200 GVA historically. And that will go down and down and down. Our natural limit at the moment sits around 100 GVA, and we have to take measure to contain that in the short term. And then in the medium term, well, we have a whole series of measures that are already coming in that allow that inertia to go even lower. So the first thing we've done and that we do is we reassess and we manage down the largest loss on the system. So the largest loss is typically either one of the interconnectors or two large units or a single power station connected through a single circuit or a single breaker onto the rest of the system. And therefore an instantaneous loss of that breaker or of that unit would cause the largest single loss on the system and a collapse in frequency. And we need to be able to operate the system and to secure that drop securely within our limits of plus or minus 1%. So we can if we reduce that largest loss, we reduce the inertial risk on the system. Alongside that, the reduction in inertia means that we're adding additional measures for regional stability and transient voltage support to improve the performance of the system during faults. We're adding inertia at a national level, as Craig said, through things such as synchronous condensers, flywheels, and through synthetic inertia. And we're widening the acceptable rate of change of frequency so that we can push the fluctuation of the frequency even harder as we go through faults and incidents. Okay, can I have the next slide, please? So just touching on the first one of those, the largest loss, the way that we handle that is as you probably know, when you have a steady state system as shown on the left there, when you have a big disturbance, you have a loss of power in feed, you have a sudden drop in system frequency down towards your operational limit. Our largest loss at the moment is contained for a normal size within 49.5, but for the largest ones to 49.2. And we're expected to be able to secure that within the timescale that the frequency falls, which typically used to be around 5 to 7 seconds, and now will be, for an instantaneous loss, less than 2 seconds. And in fact, we've split the largest loss limit into both an instantaneous loss, which is the complete loss of power in feed in less than 2 seconds, and a residual largest loss, which is typically would occur over 10 seconds to a minute. So, for example, our largest nuclear power stations tend to fall off normally quite slowly. So you'll lose the reactor, the turbine will slow down gradually, the boiler temperature will drop, and then the thing will safely shut down. Now, that's a very different loss gradually, as opposed to the instantaneous opening of a breaker and then the instantaneous removal of that power in feed from the system. Now, that faster rate of fall of frequency and that higher risk on the system means that we need faster acting response to cover that loss, which is being covered by the new dynamic containment product, which is mainly delivered by batteries. As Craig said, those markets are procured competitively and has brought lots of additional fast acting containment plant onto the system to secure those. And then alongside that, we have a very significant program that is changing lots of rock-off protection relays right around the system to expand the acceptable rate of change of frequency up from 0.2 hertz per second to 1 hertz per second. And those two measures together, both a faster acting response frequency containment and the adjustment of protection settings to allow the frequency to change faster, mean that we can continue to secure the system reliably at sensible costs in line with historic, but with a much more flexible system orientated around batteries and other fast control devices. Next slide, please. Brilliant. Alongside that, we again are looking at the level of fault in feed from the system. Now, fault in feed is effectively the pulse or support that you get during a fault, which helps to stabilize the system. And as we reduce the number of large generators on the system, the fault in feed declines, and therefore we have to contain that. The main issue we are seeing on the UK grid is effectively establishing minimum regional levels for the reliable commutation of current source HVDC interconnections. Now, they need a local strong AC signal to connect to allow them to regenerate the 50 hertz wave signal. And as we see fault in feed lowering, particularly in Scotland, with the closure of nuclear plant, then we see a drop in fault in feed that in the future may be below what we need to reliably operate the HVDCs at maximum level. So again, in those areas, we are implementing additional rotational plant, synchronous condensers, and other measures to create enough of a stabilizing fault in feed that we can continue to operate the network reliably and securely. we get a number of questions globally as to whether we have seen issues with network protection settings. And I can confirm we have in the UK with either distance or unit protection, we have seen no issues with those protection systems as we've gone to lower inertia levels, other than the fact that they are continuing to operate within their safe range, but often at levels that they haven't done before. And so we have occasionally found protection systems that have tripped because the original settings at installation were done incorrectly. And therefore they're tripping incorrectly at operating levels they've not been at before. But then we send someone out to site, we correct those levels to the ones that they should have been established at originally, and then those systems are continuing to operate fine. So again, just like inertia, we're really seeing a need for maintaining minimum levels of system inertia using similar devices such as synchronous condensers and flywheels to keep the system secure. And then finally, as I said on the next slide, we've moved away from large sort of thermal units towards offshore wind and distributed units. And alongside that, we are seeing the development of smart local energy systems. Now, John has touched on this already, so I won't spend too long on it. But we, firstly, we are seeing the emergence of distribution system operators in the UK. So that is the DNOs, the distribution networks, are beginning to actively manage their local networks and create control for local systems through active network management and through greater integration with active tools in the control room. And they're doing that because it significantly reduces the cost of upgrade and allows them to get much more capacity out of the existing distribution network as the load on that network grows, first through EVs and through the connection of more electrical heat load. Now, nearly all of the UK distribution companies have held their first tenders or established their first markets for local flexibility. They're still relatively simplistic. They're early stage, but they're going to grow really significantly over the next 10 years to manage additional connection of solar PV in some areas and to manage additional connection of load through EVs and heat in the same and sometimes other areas. We see in the UK really significant cost benefits to these smart local systems, significant avoided network investment, and you avoid additional investment in supply sources elsewhere because you can get all of the local generation away. And there is, alongside that, really significant work on, between all of the network companies, distribution and transmission, on long-term planning, on regional planning, that's aligned with the scenario planning that happens at a transmission level. And there's a very large open project in the UK called Open Networks, where all of the distribution networks are coordinating in the protocols, market design and arrangements for these smart local energy systems. And we've attached the link at the bottom of the slide there for more information. And again, I know Orkney Reflex is one of the best examples of this, so you couldn't be in better hands with Gareth and John and colleagues talking about the development of those energy systems in the UK. Okay, and near that point, that comes to the end of our presentation. Craig and I have attached some more detail and links at the end, if that's interesting, but we're not proposing to go through that in detail. We might refer to it in the questions if we need to. But near at that point, I'll hand back to you for the Q&A.
Thanks very much, Duncan and Craig. That's really, really useful and a very thorough explanation on this particular topic. So just before we start on the Q&A, we have a full 15 minutes for that Q&A and discussion. So I'll invite people to write your questions or speak straight away after this, either in Bahasa Indonesia or English. And in the meantime, could I ask Kevin, please, to launch the last poll of today? It's good stuff. As before, there are a few questions here, which is just to see what people are thinking. And I think it's also useful for everybody to see what your colleagues are also, the way that your colleagues also see a particular issue. Whilst you're going through that, can I take the first questions, please, from or comment from participants or colleagues at the Mentari or from the embassy, perhaps. I see some are already in this conversation as well. Whilst waiting for that, I have noted a question that was, I think, presented by some of our colleagues in ESDM in the ministry just at the beginning of the training, but I thought it would probably most relevant to for us to address at this session is there is this questions or thinking around what are the adjustments required, you know, between moving when moving between coal-based and renewable-based power. This is a bigger picture question, Duncan, I appreciate that. But as we've seen the UK gradually through a long period move and actually living in that transition period, there's a growing interest from colleagues in Indonesia to understand what types of adjustments have been required to and has been done when you actually move from that coal-based primarily system to a more and more renewable-based power system. And that relates to the business side of things, around purchase agreements, around business development side conversations. So is there any particular issues that you can maybe share with colleagues here?
Yeah, I mean, you could take that in many directions, can't you, Nia? But I think,
absolutely.
I mean, the first thing is that, you know, it probably started slower than we expected, but then that transition has happened much faster than our original forecasts, really, because renewables have become so cheap so quickly, and because once the larger coal units knew that they had a limited life, the investment in them reduced and therefore their reliability reduced. And then when incidents happened or there was a maintenance issue, they just simply weren't repaired and then they closed. So the first and most important aspect probably that has helped everyone has been long-term scenario planning for, you know, for the development of the grid and for the development of the associated markets around that. And alongside that, obviously the most important issue is to keep secure, reliable, affordable supplies for everyone as you go through that transition. And so to help with that medium-term commercial planning, the UK introduced a capacity market to underpin the uncertainty of revenue for a large thermal plant by providing backup funding effectively to fill the gap that gap being caused by the fact that renewables were eating away at the load factors on the large thermal units. And that's proved, we think with hindsight, really successful because it's done two things. One, it's given those large power plants financial certainty. It means that I was able to sit down with government and go, yes, we have secure supplies and I know which power stations are going to be open in 3 years' time. And power stations have both received income to support their business, but have also, in exchange for that, have given contractual assurances about whether they're going to be open or not for the next 3 to 5 years. And that's been incredibly helpful then using those scenarios to plan. Now, alongside that, the arrival of much more distributed energy, which I think also you'll see in Indonesia related to solar, has created the need to standardize and reform connection arrangements to make sure that the grid code provisions, both technical and commercial, are appropriate for the new generation sources that are emerging. And I think probably between the year 2000 and 2005, we spent that time in the UK fighting the increase in renewables. Gareth will probably tell me this. He used to phone me up and tell me off, and trying to force renewables to comply with standards that were developed for a coal and gas-based system. And from 2005, effectively, we changed our mind and we decided that instead of fighting it, the way to deliver a secure, reliable economic system was to adapt the technical standards and the commercial standards to take advantage of the technical performance of the new generation technologies that were coming on. And sometimes we've done that up front, like connection and technical performance standards for wind and for solar with regard to frequency and voltage, which Spain got wrong. And sometimes we've done that with hindsight. So even today, we have a requirement for all generation types to follow a physical notification that they submit 1 hour ahead of real time. But we explicitly have said that we won't enforce that on renewables because that would be stupid. They should just do what they can based on the weather. And actually, our forecasting is good enough that we would then adapt physical control of the network based on what we know they're going to do in real time, not what they told us 2 or 3 hours ago. And that's we considered an appropriate economic adjustment and something that we didn't need to spend years talking about. We've just done it and we've told people. So, and I think that combination of long-term scenario planning, which helps people understand how it might occur, but it will be wrong because forecasts are wrong, combined with policy measures to underpin and support the businesses through that transition. And then that mindset shift to adapt to the changing technical environment rather than try and force and limit the change into your existing technical standards. Those three things have been really important at helping, not helping it happen at too fast a pace, but helping it happen at a responsible and controlled pace where we can give assurances to government that the costs and reliability will remain in line with historic levels, but it's allowed competition and investment and growth to really accelerate.
Thanks very much, Duncan. That's brilliant. Gareth, I saw your bat on straight on the comment, so I'll invite you to just speak directly if that's okay, Gareth.
Yeah, no, it was really, I didn't know how to get my hand up. So yeah, I was just thinking, Duncan and Craig, that in the UK we've had a particular situation where our coal power plants and existing power plants are in quite space constrained areas, and when we look at Indonesia, despite there being very dense, tightly packed areas, there are other parts of it where there is space around these plants, perhaps for cogeneration to take place. And I just wonder whether that might, do you think, help the situation whereby that the nucleus for jobs and employment and as an energy hub in the system can still exist. It's just it might transition from being a coal-based hub to another form of energy. Do you think that could be a significant benefit or actually not that important overall?
Yeah, well, I mean, these things always seem like a good idea, don't they? But actually in the UK, they've rarely happened. So we've seen a big shift from the power stations in coal fields to offshore wind and indeed solar in the south, so which has completely changed the network flows in the UK. And I think, a bit like your poll earlier, probably the most important design contingent for the power system is the availability of resources, isn't it? So, and we've seen, and I think we've seen planning as a huge driver of the management of those resources in the UK. So, particularly in the growth of onshore wind in Scotland and of offshore wind right down the North Sea, down the east coast. Those two things have really been driven by availability of resources and the ability of the planning regime to allow those to connect. And the transmission grid is only 4% of the bill. So actually it's been more important for the transmission grid to move as quickly as possible to get out of the way, as it were, to facilitate everyone else playing their part in the investment chain. And my major concerns over the last 15 years have not been due to reliability or security of growth of renewables. My major concerns have been where the transmission network was stopping investment and growth in other parts of the power sector. And when it does that, it limits jobs, it limits opportunity, and it limits the transition. So I've seen probably the most important interventions that the executive team have made have all been around creating the right environment for rapid investment and development in other parts of the power sector, and providing that bridge to government to show that you can do that in a reliable and secure way with sensible government policy as a backbone to that. That's probably been the biggest challenge for Gareth. So, I mean, yeah, you can, where you can, brilliant. And definitely we've seen things like batteries co-locating into similar sites where there was historic generation. But for renewables, the most important thing has been to put them where the best resources.
So can I follow on, Nia?
Yes, you can,
Yeah.
Gareth. Of course you can.
Thank you. So yeah, I mean, I think you've given a fantastic description, really, of the journey that we've gone on as a country in the last 20 years. And I guess one of the things is that we haven't got another 20 years to make that same journey in all of the other countries of the world. So on reflection, with all of that learning that we've got, is it simply a case of other countries following our pathway, or are there smarter journeys that can be followed, basically? You know, if you look at somewhere like Indonesia, do they simply repeat what we've done, or actually could they take a slightly more effective and efficient pathway, having learned from our experience? I guess that's my key question.
Yeah, of course they can. Yeah, I mean, and they will create their own. You know, Indonesia is a sophisticated and complex country with its, with its own democratic processes to manage some of these really big transitions. It's really important they do it in their own way. I mean, my message would be probably that the big steps in the UK happened in two big leaps. One was the growth of onshore wind in 5 years, probably from 2005 through to 2010. And then the second one was this big leap in offshore wind from 2015 onwards. And actually, the bits building up to that were really around getting the cost of those resources down, and now that those resources are much, much cheaper, I would hope that Indonesia can move much faster. And actually that creates a transmission, that creates a challenge for the network businesses in Indonesia, because the potential growth is now much, much quicker. So again, getting ahead of the planning curve and working really closely with regional government and national government on how to manage that growth with local stakeholders in a democratic way is really, really key. And a very good relationship between, well, I'd suggest with PLN and the national government in terms of how that can happen would really, really help. And I think network development always takes time. In the UK, it takes 10 years, but in South Africa, it takes 10 years. It seems to take 10 years in Vietnam as well. So wherever you go, it takes time. Yeah. So making the most of the existing network through good forecasting, through adaptive engineering policy and practice to get the most out of the existing network and that helps underpin investment and the growth in the resource. Then the transmission network and the growth in networks can come later. But Indonesia has this vast and fabulous potential. It's bigger than Western Europe, so it feels odd to talk about the UK experience when Indonesia is such a larger country with such a larger potential growth in demand. So we certainly, Craig and I, wish you the best of luck with that, and would encourage you to do as much as you can whilst allowing the network to grow.
Brilliant, Duncan. Okay, so that takes us towards the end of this discussion session, actually. Can we close the poll, please, Kevin? And maybe we'll have a quick look on what the results is before we close the second day. Good stuff. So most of you think that it is the environmental drivers, excuse me, that is the main driver in pushing the agenda for renewable energy, and then there's it's followed very closely by the economic drivers. The second question is around the main challenges in integrating renewable energy into the energy mix, and most of you think that it's around reliability and then followed by accessibility. On the third question, where would you think that renewable energy can play a great role in providing access to electricity for economic productivity? Most of you think that it's in the remotest islands, and then followed by, well, actually, as well as the remote villages, and then industrial zones. That's a very interesting last poll of the day. Thanks very much for that poll. So yes, we have reached the end of day 2. Thank you very much for your time, both for the speakers and the participants, all colleagues in the UK and in Indonesia. So Duncan and Craig won't be with us tomorrow, or you're very welcome to join us as well, but you won't be both of them won't be presenting to hear more of Indonesia's massive challenges, and wishing us luck with that. That would be anyway. So yes, and definitely we should follow up with a more advanced session, planning session for the different detailed workshops follow up later in this year. So I'd like to say thank you once again, Duncan and Craig, and also Gareth and John for your time today.
Thanks, everybody. See you tomorrow.
Thanks, everyone.
Thank you. Just one last remaining messages for those of you are still online for the second session. Any further questions can be followed through to agungiswadi@aquaterra.co.uk. We'll take questions offline. If you don't have time to put them on the chat box, please send them through and we'll try our best to circulate the answers. Thank you very much.
Thank you.
Terima kasih.